Okay, so I made a few changes which are actually consistent with what I said at the beginning of the semester, and then I forgot a couple weeks ago when I said your final paper would be due this Thursday. Your final paper is not due this week. Your second draft, which really is your first final paper, right? The first draft was a very rough draft with lots of stuff missing. Now I expect a complete paper by, I think it's now the 13th. I wanted to give you at least 1 week after I finished giving everybody feedback, and it took me a long time to get through everybody to give you feedback. So hopefully by now everyone has gotten some feedback. Some of you got a lot more than others, depends on how rough it was. If you didn't understand my feedback, because sometimes I'm somewhat cryptic, send me email, we can chat about that. I'm going to be out Wednesday, Thursday, Friday this week, so you can maybe meet me tomorrow, but if you send me email, I can sort of explain where we're at. So your assignment this week is to finish your paper, okay? And you may think it's finished, but you're then going to, on the 13th, when your paper is due, we're going to be doing peer reviews. So each of you will be reviewing 2 other people's paper, and then you will get 2 other people's comments on your paper. So sort of a swap process. There'll be 4 days to read those other 2 papers and give them feedback. And part of what we're going to talk about today is the process of getting feedback and also reviewing, so it's a general thing. So you have an idea what to do with that. But this way you'll be getting somebody else's more detailed comments, but also different points of view about your paper that you can then use to make your final paper. In terms of, and then I'll also be grading you on the comments you give other people in terms of are you giving good feedback and what are you doing with that. So any questions about that? Yes, so I'm trying to figure out how to do that because some of you are in teams and some of you, for example, other people may have a hard time with your paper. But we'll see. So I guess we could actually, we did talk about having people choose who they want to peer review. Maybe I'll do that. So how am I going to do that? I think I'll just assign them. I'll take the people I think are most likely to be capable of doing stuff, and I'll make those assignments. So, and at a certain level, it's a survey paper. So even if you don't understand battery or hysteresis models, you can still make some comments about the paper overall, right? You're all smart enough, you can make something about the paper. And it's a survey paper, so you're not actually commenting as much about the core mathematical models anyhow, as you are about the way the paper presents stuff. And similarly, if you get assigned a paper on natural language, you'll make something out of it. So anyway, so the 13th your draft is due, and then you'll have 14, 15, 16. Sometime next week your drafts will be due, and then I'll give another week after that for the final version of your paper. Okay, but by then it should be tapering off, and we'll be moving on to other things. Okay. Any questions, comments? No. We're talking about the paper, right? The bibliography is, so in most of our conferences now, it's 8 pages plus whatever you want for references, whatever, so that should be fine. And very important, because for at least 2 of you, you were cutting things down to hit the number of references I said. You do not have to cut down the number of references. That was a minimum. Same is true with page length. If you actually feel you want to write a 30-page survey paper as this, I'm okay with that, right? I'm just not setting the bar that high, but I'm not going to make you make it really short, but you can make it as, at the length, depending if you're a team or not, at whatever we set that at. So those are the minimums where it's going to go. I don't know. So I will read them. So far, the grading has been more on your process than the content, right? So the grading for your final paper, which will then do things like, did you incorporate or reasonably address the reviewer's comments? So there'll be some of that, but mostly will be like, did you actually hit the objectives of writing a survey paper, having a reasonably good way of looking at the world and whatever? It's not a question of whether or not it's publishable, right? I'm not holding it to that highest standard. Did you, tell a story, right? Those are some of the things I'm trying to push you to do. If you do those things, then the grades will be, high. And if you miss major things, so I mean, some of the people in their drafts, we had drafts missing lots of the references, right? That's going to be a problem, right? So you need to hit the sort of guidelines for what the paper has to have. But I would expect all of you will be able to get an A. I'm not grading harshly, right? This is not like my undergraduate classes where I push them very hard and I grade on a B- or a B average, right? I'm grading on a graduate student average for which B is barely passing, right? For a graduate student, but most of you, you might have, I mean, if you look at the grades you've gotten on your journals, right? I think the lowest grade I've given out so far in a journal is a 7, and that was a 1-sentence journal. So, you know, if you're working in your process, 7s, 8s, 9s, 10s, right? If your feedback on your draft, and I don't remember yours being problematic, so if your feedback was you are really far off of this, right, and some people were told to come chat with me, right, then you've got a lot of work to do to catch up. If if your draft was simply inadequate, then you might have a problem. But this is not. Is it publishable? And a couple of people asked me, like, is your paper publishable? I can't answer that right now, especially if it's outside of my area. But even then, it's still a draft. At a draft level, no, it's not publishable. None of them are, right? You've got to turn them into real papers. Okay. And if you have not, although I said a particular, like IEEE transaction 2-column format, that's just when I say pages matter. If you really want to do it in some other format by changing your LaTeX style because you're aiming for a particular journal, that's okay as long as I can approximate the length. So if you go to a NIPS style paper, it like doubles the page length or whatever. Depends on where you're aiming. I was a NIPS conference, you wouldn't be aiming there. But so I want this to be as useful for you as you can. So if you're spending time and you're aiming for a particular journal, if you have not actually targeted a particular journal, you might want to, because that as you're writing your final version, you've got the core story and whatever, but the style of writing might actually, if you're looking at ACM computing surveys, it's different than if you're looking at IEEE communications and tutorial surveys. And if you're looking for a conference, you're going to want to balance those out. So if you're looking for something that's got a 12-page limit, including references, we can talk about that, right? You can probably still make 8 pages plus 2 pages or 4 pages of references. That'll probably work in terms of where you're going. Okay. So we're going to actually start today with reviewing and giving feedback, since that'll be part of your assignment for this. Come on, go back. That'll be part of your assignment this week. This is based on a bunch of material from various places, but when I steal PowerPoint slides and other material, I like to cite them, so at least they're somewhere here. So I'm going to start with this from a peer review point of view, and then we'll actually talk about it from a reviewing from an actual conference point of view. And the reason for that is a little bit different. You're not here making recommendations of accept or reject, so you don't have the same role to play as a reviewer. So some of it's the same. But my suggestions in terms of 6 steps are really pretty much the same for either one. The first is to skim the paper and make a few notes. And we'll come back to how you're going to use those notes. But if in your 2 to 5 minute skim, you don't get the gist of the paper, you want to actually be making notes of that because you're going to give people feedback. Then we're going to talk about critically and creatively reading it, summarizing it, which is now, so the first 2 are your reads. Then it's how you write your review and give your feedback. So in your first 3 to 5 minute skim, you're going to make notes on what you think is the core of the paper, the high-level issues, and if that made you want to continue. And you're pretty much going to try and write a couple of sentences about that. So why do you think this is an important thing to do for giving peer feedback? This, by the way, is the one part you don't normally do for a conference paper, but for peer review, I think this is really important. Why do you think I want you to do this skim even though you're going to read the paper in detail anyhow? You have no choice. No, it's following the process, but so I'm telling you to follow the process, but why do you think that's part of the process?
Is that the way reviewers look at it?
Well, whether or not it's the way reviewers will look at it, it's definitely the way many readers will look at it. So if in the skim of the paper, the reader can't get the gist of the paper, you're telling the authors, here's what I got in my 2-minute read of the paper. If that's not what they intended, then they're not conveying their message properly, and they need to get that feedback. Not if you read it in detail will you get it. You need to get the quick thing, because that's the way lots of people will be going through their papers. So that's sort of the fast read, and if that's not it. But many reviewers will also do that skim. So they want to get, here's the general view of the paper, and figure out what are the core issues you're trying to highlight and get to. So at this point, you might also note any questions you had at this stage. So the 2 or 3 sentence summary you're going to things. Try and find at least 2 positive things to say. This is actually another thing I do as a reviewer. When I really review, I do my scan. I'm trying to find what are the things I think are good in this paper in that short period of time. Right? I actually don't try and be critical in my scan. The scan's only trying to find something positive. Because it's easy for me to find critical things. It's hard for me to find a positive one. So the next is what I would call step 2A, and when actually I do 2 passes of the read. And I want you to be careful about this. Spend a maximum of 30 minutes for this assignment reading a paper. Right? You could spend 4 or 5 hours. The papers may be farther outside your area. There's a lot of stuff going on. That's okay. So you're gonna have to still balance your time here. And if you can't get through the bulk of the paper in 30 minutes, make a note about how far you got in terms of your actual critical read. But be willing to skip over some paragraphs. It's like, okay, I see what this paragraph is doing, right? I'm jumping on to the next one because you're falling behind in time. I don't want this peer review assignment to be too long, but you can also be telling the author, right? What does it mean if it takes you really long to read a paragraph? Maybe that paragraph needs to be restructured, rewritten. It's really hard for you to figure out what's going on. So there's some of that to do. So as you're reading it all, take notes as you would in your own personal critical read. If you use a paper or PDF, you can mark, circle, highlight areas with issues. Okay, I'm not looking for you when you're doing your critical read to retype paragraphs and whatever. And as you found when you're doing your scans, especially when you're doing your quick browse, you spent almost as much time doing bookkeeping as you did doing the browsing sometimes, right? That's not the goal here. So my recommendation is if you're a paper person, have it printed out. And then if you get to sections where there's something weird going on, your paragraphs are awkward, you can just circle the paragraph and say awkward, right? You don't have to actually try and fix it. Your job is not proofreading, right? This is reviewing and giving feedback. So go through it that way. You don't have to describe the issues in details. If you get a paragraph back from somebody that's got a big circle around it, you know you got to rework this paragraph. Exactly why? You can figure that out on your own. But if you notice things, go ahead and make notes of them, but you have to balance how long that's going to take. So you don't want to spend a lot of time. Your primary point is not telling them about fixing grammar if the section needs to be rewritten. Your job is not to rewrite it. It's not even to necessarily say there should be a comma here or a comma here and quotes here. You can put a couple of those in if you're really feeling up for that, but you're really giving your critical read is more about the assumptions in the paper, the style, the story, the elements. That's what you're trying to help them fix. And then do the creative read. Find the core of the story that you think works. What do you think about this paper is really helping, is really working? Find multiple positive things to say. Include creative reading. Include your usual creative read process ideas. So how might you build upon that is a perfectly good thing to be looking at, how it might be combined with things. Try to think of ways to make the paper better in your view, but remember you're only one reader. So, don't say, you should change it so it's better suited to me, right? You might phrase it as, right, some readers might find it, better this way, but recognize they might be aiming at a different audience than you, because for most of your peer reviewing, you are probably not the writer's target audience. So if it seems a little too technical, that's probably okay because that's not your area where it's going to go. But if you couldn't understand any of it, then it's probably not, because not only do you want your Oscar to start broad and come in terms of area of impact, you want it to be understandable by everybody down to where it might get too technical. Okay? So you'll notice in my suggestion, you actually looked for positive things first, did your critical read, and then you look for positive things again. That's also really important because my experience, both as an author and as a reviewer, is most reviews are dominated by the negative things. It is easy to criticize. It is hard to find positive things. So you're going to do that twice just to increase the chance you'll find something. So at this point, you have your notes. Now it's time to actually write your review. So you're going to summarize the 3 or 4 things you think this paper is about. Generate a 3 to 4 sentence summary of what you think it's about. Very important, and this gets really annoying when you're an author, don't just cut and paste sentences from the abstract to use as your summary. In fact, my recommendation is don't even look at the paper when you're trying to write the summary. You should be doing it from your notes or from memory, right? Not looking at here's what the paper says the paper's about, because they already know they think that's what the paper's about. Those were their sentences. If you use different sentences and you don't capture what they think the paper's about, they actually get lots of useful information about the writing, right? I thought the paper was about this. The readers thought it was about that. That's a communication failure, right? But if you copy their own sentences, they will interpret the sentences the way they think the sentence is meant, not the way you might interpret the sentence. So you definitely don't want to do that. If your scan and detailed reads are different, have a sentence or two about those differences. So in my first read through the paper, I thought it was this. Later, when I got into detail, I recognized it's probably about this. And the paper needs to somehow, come to terms with what those differences are, right? At one point, if you get 2 different points of view, you're not even sure which one's right. If you read it, even if you read it 3 times, right? At one point, it just seems to be inconsistent. So you got to tell them about that so they can try and fix it. So after you have the summary, the goal of the summary is not to say what's good or bad. The goal of the summary is to provide a summary. here's what I think the paper is about. The paper's contributions, are this and whatever. The next step is to sort of give them some compliments. This is both feel good, but also letting them know the things you thought were most important in the paper. And I'll come back to this when we do real reviews. This is about helping them. So you want to be positive and constructive. So you don't want to be, the paper was great and think you're done, right? You have to tell them, what about the paper? Be as specific as you can about the parts about the paper you think were really good. And that's going to become important because when we get into the negatives, they got to figure out what parts are good and what parts are bad, right? So things like the significant part of this paper was the whatever, right? Whatever you thought was significant, right? I really love your story because, give them some details. And then you can even get into details about the style of presentation. I think you use a lot of supporting details for this comparison, or I liked your drawing that helped me understand this. Just tell them what the parts that were there that helped you feel good about the paper. In our reviewing, we actually have, depending on what conferences we run, for the positive section, I guess we'll get to that when we get to the sections. We have minimum word length for this section now because people were just saying, paper was well written. That's not enough. You wanted to give them some details in there. So the next step is suggestions for making things better. And when we get to conference reviewing, we normally break this up into two categories. And those two categories are suggestions, which are high level, and then corrections, which are low level. So major and minor suggestions, corrections, they'll go by different terms depending on where you're looking at. But you still want to be positive even when you're saying this is broken. So instead of saying something like, it didn't make sense, which is actually something I might say frequently, right? Try and say, if you added more details after this sentence, it might be clearer, or this section might be clearer, right? Tell them where. If you can't make any sense out of it, you can go ahead and say, right, I couldn't make any sense out of this paragraph, right? And when I'm reviewing, sometimes I will describe paragraphs as word salad, right? They're just a jumble of words. I don't know what they mean. But try and be, and sometimes if you're trying to be funny, humor can help, but you want to be pretty positive. If I'm in a very dour mood as a reviewer, sometimes I will say negative things, and it just doesn't help as much. If you're writing comments about things, try and be very specific about where it is. The page, the paragraph, the column, the line. In fact, in many of our papers, when you're doing reviews, all the pages are numbered with lines on every page. And line 37 is on the first page here. Line 300 is on the whatever page it is, right? So you can refer to a very specific point with just a couple of characters because we're trying to be efficient. But otherwise, you can say on page 3, column 4, second paragraph. I have no idea what these equations are trying to tell me, right? Something like that. And that really can help the author. Now, if you're doing it with physical things, right, you can circle some stuff and put a little number or a mark, and then you can have comments that refer to that, just whatever you're trying to do. We don't want you to spend a lot of time. We're just trying to maximize the feedback you're giving. So you can be very specific. Perhaps using an analogy to something else would have helped the reader understand the way your formulas work. I didn't understand the sentence about whatever. I found your arguments about something confusing or weak or not convincing, right? Whatever you're doing. Your conclusion was too short, too long, too obvious. Your statement was something statement is an extraneous detail. It doesn't really matter. It's unsupported or wrong, whatever. A citation might help, right? So try and turn them around and give them some positive feedback, but also suggestions, because it's easier to take in a suggestion and say, this is how I'm going to make my paper better, than to say, they just circled this paragraph. Now what I'm going to do. Now, even giving them the circle is a lot better than where they were before, but the more details you can add there is better. So the last step, which is not as critical, but can be very helpful. And if you're dealing with somebody who's writing a paper in your lab, and you're like a co-author, well then this is required if it's something you can do. If you're still giving someone in your lab, right now you really want to make corrections to suggested edits. So simpler things like spelling mistakes in grammar, missing punctuation, incomplete or run-on sentences. Sentences that take half a page are by definition a run-on, right? I write them all the time. So you want somebody to sort of highlight those things as well. Not as critical for this assignment. For many of you, English is not your native language, and my writing in any other language would be completely non-understandable. But even my writing in English is generally non-understandable in the beginning. There's lots of these things that people have to you count on people to help fix. But so make some of these if you're up to it. It is not required. when you get reviews, if they don't tell you about grammar mistakes, it doesn't mean there aren't any. It just means that as a conference reviewer or paper reviewer, they weren't getting out of that level of detail. As an editor for a journal, we actually explicitly tell most of the reviewers, don't worry about grammar, right? We will, if they notice grammar issues, if they say this paper needs grammatical thing, we recommend the author pay a proofreader, right? And some journals actually pay them themselves. Other times the author is expected to do that, but somebody who's a professional proofreader will find a lot more grammar mistakes than most of the technical readers anyhow. So it's not like it's going to save time and money. If the journal feels it needs to be proofread, they're going to demand it be paid. You have a real proofreader, not just the ones the editors find. But if reviewers find a couple, that'll actually help set the tone that they needed. So now I'm going to turn this around a little bit. So I want to start with that process, which is the process you will use for peer reviews. Any questions on that? Now I'm going to talk a little about it more from a conference journal peer review process, because you may all understand this. And it's also good to understand that this is pretty much the process, and websites for any major conference almost always have instructions to reviewers. You'll actually find some of these are embodied in the instructions to reviewers that in some of the conferences I've been a part of. So the sort of standard review items, they change the names around a little bit, but and the title and author is normally pre-populated for you, but sometimes for journal reviews, you have to type it in yourself because it's a blank form, you got to fill it in. Summary of the paper and its contributions. So this is the 2 to 3 sentence summary, just like we talked about for the other one. But for journals and conferences, they normally expect you to also highlight the main contributions in that section. And again, it's not a cut and paste of what they thought were the contributions, it's what you thought were the contributions. Positive things about the paper, minimum 1 paragraph. You should always find something. I'll go through these in more detail. And then there'll be the weaknesses. And then there's also room for private comments to the program committee, the area chair, the editor, or something like that. So here's sort of my paper reviewing algorithm, right? So you're going to read the paper, you're going to think about it, and then you're going to sort of write a review. Okay, those are the 3 key things you're trying to do. But realistically, I read the paper, or more likely, I listen to the paper. I think about the paper for a while. I start writing some of the review, and then I go out and I take a look at related work. I leave it alone for a few days, so I must always do my reviews and then let it sit for a couple days, see what other, right? Read/listen to it again, and then I rewrite the review. So just like writing a paper, it's not actually sit down and write. It's generally not. It's think about it, work on the story. Well, in this case, I write the first time I write the review. I did the scan, I did the quick read, I think about it. But then I also have to relate it to other work, which is generally not the same day, in part because very often I listen to the papers while I'm in a place where I don't have internet. So I listen to a couple of these, then I'll go do some research and figure out what to say. So I write the review, and then I'll rewrite parts of it as I go back and do the searching. And I'll come back to that as we get into details. So when I think about it, it's really about trying to understand what's the paper trying to do? What's the observation, the motivation? Programs often do X, in the future Y won't work, there's going to be some problem. Okay? And I try and think about it not just from my point of view and not just from their point of view. I actually try and, what's the broader audience going to think about? I have plenty of papers that I read and I review that I would never choose to read. Right? That doesn't mean I should reject the paper. Right? I was assigned this paper because I have the ability to review it. Whether or not it's something I would choose to read is a different question. So the review is not, do I like it? It's, will other people like it? Can I see a large enough population for it? Looking at their implementation, here's how I might exploit their observations or somebody else might exploit their operations. Looking at the evaluation, what are the sort of things I think about in ways that might make the paper better, what I didn't think work and why. Right? All of that is what I'm thinking about the paper. I'm not reading it, I'm not comparing it to anything else yet. And I like to think about the entire paper. That's the other reason to do the scan first, is I have an overview of the paper, then I can do my read and I have a feel for where it's going. And inevitably for me, that's actually thinking. Inevitably when I'm doing that, there's not a place for me to write down or take notes. So I just have to sort of think about it and remember it, but that's my style. You might actually find taking notes during that process is a really good thing. And if I actually had time on the computer, I might actually be doing most of them that way, but I might be riding a bike or flying in a plane or whatever. So contributions. some of the things, so this is the list I don't actually use, but it's a list you might think about when you're reviewing, and reviewers sometimes are given things, right? Did you gain an important insight? Is there a new problem, a new way to look at a problem, something that's counterintuitive or unexpected? You'll notice that if we think back to success, right, these are all about something that is unexpected in one sense, or at least two of these are about unexpected things. And that's actually an important part of the novelty of a paper. If you gain an insight because you hadn't thought about it, even if the rest of the paper is wrong, well, actually, not if it's wrong. If the rest of the paper is incomplete in its analysis, it might still be worthwhile. Because just to describe and attack a new problem, even if the solution is not great, is a useful thing. For a new problem, less important, but for any problem, did it propose a good solution to the problem? Did it explain why the solution should work? Did it explain why it's better? In areas where, for example, with neural nets, right, we might not know why it's better, right? There's no good suggestion. But if you don't have a theory why a paper is better, your paper is in trouble as a writer. As a reviewer, if they're not explaining to you why you think it's better, right, it's possibly better because they had a bug in their experiment, right? And it's not that they're intentionally trying to hide something. I've had bugs in my experiments where we swapped two variables and got amazing results that we couldn't explain. And the saddest part in retrospect was the first time we suggested the paper, they rejected it because they said, you have no explanation why it's this good. And so we went back and paper was rejected. We worked hard on it. We invented an explanation. Paper got published. That explanation actually was still slightly true because we showed it more formally for another set of problems, but it didn't really explain that phenomenal performance on one problem. That was just a bug, right? Nothing was explaining that. So, so you're looking at the paper from the reviewer point of view. Do they have a compelling solution of why it should work and how you're going to put it together? Did it have a good quantitative evaluation? And this is another common thing. You might think when you write a paper, we have a good experiment. As a reviewer, you're going to say, how good was that quantitative evaluation? So should it work in the with real processes? Will it gain or lose relevance in the future? And will it work in real applications? All of those are things about the secondary parts of the application. But if the paper doesn't statistically analyze it, you might say, well, the experiments were okay, right? If they're running on, and there are papers that do this, I get a couple every year, they claim to be state-of-the-art using a database that everyone stopped using 5 years ago. So there is no paper published on that data set that is better. So in one sense, their statement is true. They have this state-of-the-art on that data set. But the data set is so small and antiquated that no one's even looking at it anymore. Now, if they took the current state-of-the-art algorithms and ran it on that data set, then there might be something interesting about that sub-problem. But if all they did was take the results from 5 years ago that were published and say we do better than them, then your qualitative evaluation might say, yes, that's not using state-of-the-art data or algorithms. So when you're thinking about looking from the contributions, these are, if you can answer yes to more than 2 questions on this page, then the paper has some real contributions. If you can't answer yes to any of these, then find some contribution. My guess is, maybe it doesn't have a good qualitative evaluation, but maybe there's some examples that suggest maybe it will work, right? So maybe there's something in the middle, right? You'll see where it goes. So the summary, which is a required section in all of the places I review, is a 2 to 3 sentence summary. It's like a very short paper abstract, but importantly, it's short and self-contained, no undefined acronyms. You can use any acronym they used, obviously, but don't have new ones. It's a short, high-level description of the contribution. Don't copy it from their abstract. Again, that's the common thing we see is people just copying it from it. But this is not quite the same as their abstract because there really is no sales pitch in your point of view about whether it is state-of-the-art. This is your evaluation. If you think it really is state-of-the-art, fine, go ahead and say it. But this is about trying to make it sound good. Your summary doesn't need to quote numbers they already quoted, right? The summary is so that they understand you understood what the paper is, and really it's going after what really is the contribution in your view, right? Which isn't the number. It's always advancing something along some dimension. You want to hit the positive contributions and good points. So if you've learned something, that's good. That's a contribution, even if it's not what they said was a contribution. Okay. If it can be used for real systems, that's good. If you see contributions they didn't claim, you should definitely put them in this section. And then you're going to want to list the most important things that they might have said, but in your own words. If the only thing you can say about the paper is it's well written, it's really bad. Okay. Now, unfortunately, there are many papers when I review where I struggle to find something positive to say. And when it's been, the 8th paper I've been reviewing this weekend, and sometimes I'm not in a good mood, I might not say much more than 1 or 2 sentences. But you always find some good points. As I said, a number of our conferences now, we're putting minimum text length boxes, right? So you can't leave them empty. You can't have less than 500 characters in your description of the positive things. You got to find something. And then we stopped, I don't know, I think this year CPPR, last year CPPR didn't do it because all we found was people were cutting and pasting things from the paper, right? Because if you make a reviewer's job annoyingly hard, that doesn't make them do their job better. It makes them find ways around whatever you told them to do. So the weaknesses, the bad points. These are what I call major weaknesses. These are the things that are really reason to reject a paper. Even if it's got some good points, the bad points might overweigh it. And if you're dealing with a highly selective conference where 25% of the papers are going to get in, enough weaknesses may move it down from acceptable to unacceptable, not because it's not acceptable work, just because there's better work. So you got to figure out where that balance is going to be. Big problems, like motivational problems. If it's unclear whether there is a problem or why it's an important problem, right? If the paper is purely academic, that is, no one in the real world would ever care because you invented a problem, right? So then maybe it's not a paper worthwhile. But maybe being purely academic is okay if it's an abstracted version of a problem that goes across many things. So it's up to you to explain what that motivation is and why, or if it's insufficient. Implementation problems, if it's unclear why it would solve a problem this way or unclear what the trade-offs are. Now, this could simply be a typo, right? This happens all the time. People have pseudocode in their paper or whatever. You read it and it's like, this can't possibly work. Well, that's an important feedback for the author, even if it really just is that their pseudocode was broken. Maybe the idea works fine, but as presented in the paper in pseudocode, it's broken, right? You got to figure out what those are. Evaluation problems. There's all kinds of things that can go wrong with this. Insufficient amounts of data, insufficient comparisons, comparing against the wrong thing. Any one of those might be where you could have problems that are enough to kill the paper. Organizational problems. The paper is difficult to follow. You can't make sense out of what's going on. It's jumping around. If you really can't even finish reading the paper, it's a major weakness of the paper in terms of its writing. You have to be careful, though. You might feel the paper is unreadable because you simply don't have the background, right? That's okay. You might even say, given my background, I can't read this paper. Of course, that doesn't help the author very much because they don't know what your background is, right? You might say, as somebody who's published, only 10 papers in this area, I just couldn't follow these arguments or whatever, right? And then they might say, okay, well, I'm aiming for somebody with a little bit more experience, right? See where it goes. In this case, this is one of the places where when I told you I write the review, then I go back and rewrite the review. This is a section that often gets filled in because one of the other things in terms of the evaluation problems or motivation problems is the relationship to prior work, right? Especially when I get a paper that's not in an area that I publish on regularly, but maybe I published on sometime in the past, right? I might not have been keeping up in this space. So when I read it the first time through, I'm not thinking about those 3 papers that came out in the last 2 years that I didn't know about. I have to go look for them. Your job as a reviewer when you're reviewing for a conference includes looking up those references. If the author says they are state of the art, you want to verify that claim, right? So that comes back into sort of evaluation or motivation. Maybe I want to look at it. So I'll go back and I'll do more of these. And then I actually try and list these in one of 2 orders depending on what I'm dealing with. So it's convenient to list them in the order they occur in the paper, especially when I'm doing my critical read of the paper, right? I'll just put them down in order. But then I will rearrange them into groups that are in temporal order of the paper. But mostly, here's the 3 most significant things. These are the biggest things. Then sort of the next group of things that are important but not critical, right, that you might get there. So there's some questions to ask yourself when you're looking at a paper when it comes down to making your final recommendations. In many of the reviewing for conferences and journals, there is an expectation of the reviewer to actually ask the authors questions, right? In most of our reviews for major conferences in my field, we actually have a section of the review separate from weaknesses, which is questions to be addressed in the rebuttal. Our conferences have a rebuttal process, so a little bit like a journal, but not as formal. Authors write a paper. Reviewers reviewers read the paper, make comments, ask questions. Authors get a chance to answer some of those questions. Then the reviewers make a secondary review and make a recommendation, and then the paper finally gets decided on. And the reason for that is we learned early on in the process that authors write something, reviewers sometimes completely misunderstand what's going on. And a few answers from the authors can set everything straight, right? And sometimes you'll get reviewers who will write very, very negative things. I've seen papers go from a 5, which is the worst possible score, to a 1, right? Where the author's writing or whatever, or more likely the reviewer's misunderstanding, caused them to think this is like completely bogus. This was done in that paper, right? And then the authors write back, no, that paper was proven wrong, and so it doesn't solve the problem, or whatever else is going on. So understanding these questions can be important. So if answers can't change your recommendation, don't ask those questions, right? If you say, well, I didn't understand this paragraph. If understanding that paragraph is not going to change your interpretation of whether or not the paper should be accepted or not, don't put it in the section for major weaknesses. Put it in the minor section, right? It's good to give the author that feedback. So that's the other reason why when I'm doing this, I'm often doing, right, I'm writing down my questions. Then I'm going to sort them into really high-level major things. These are the most important ones. Important things that might affect my decision, and then all the other things that will just go in another section called minor or general comments. This one's a little trickier. What happens if it can't be answered in a few days? So if I'm saying, well, this paper simply needs to run this experiment, which will take 2 months, right? Then yes, it's a major concern, and it's not going to happen during the conference reviewing cycle. But for a journal, that's a perfectly reasonable amount of time sometimes for them to deal with it. So you got to figure out what's the time frame in which they're going to answer it. And the other thing which conferences are changing, so CVPR and NIPS both are starting to rein in what reviewers can ask for, in part because everyone is now playing the game a little bit differently. When we submitted our NIPS paper, the week after we submitted it, we sat down and said, now what are the 4 biggest questions we think they're going to ask us and experiments they might ask us to run? And between the submission of the paper and the reviews, we actually ran a bunch of experiments, anticipating their questions, right? Because then we can turn around in 4 days a question that would have actually taken 2 weeks because we'd already done the computations of those. So sometimes what you think might take longer might still be okay because they will have done experiments in between. They submitted the paper often 3 or 4 months before you're finishing your review. It's also really important if you're not sure you got something right. If you're reviewing, especially as you're younger in your reviewing process, right? If your decision depends on an interpretation of something that you're not sure about, then make it very clear and ask this as a question, right? I didn't know. So don't say the question, if this is true, I'll accept the paper. If this is not true, I'm not going to accept the paper. That's just asking the authors to tell you what they think you want to hear. But you say, right, I really didn't understand this, and I need the authors to answer this question. Because if that's going to help you decide what you're going to accept, you're going to do that. Okay, so do put that in that kinds of question sections to answer. And then the last section, which is actually, for me, almost always the bulk of my review, in part because the major section should only be the major things. If I have 5 or 6 major things, that's already enough. The paper may be dead. I'll put everything else in minor. So the minor comments or minor weaknesses or general comments, this is always where you're there to help the authors improve the paper. Be as constructive as you can. So if instead of saying a cache conflict with 1024 way set associative caches, is useless or something, right? The author should focus on lower associative caches, right? Don't tell me why 1024 is useless. Does that mean I should have bigger or should I have smaller, right? You got to give me meaningful feedback to try and make that. Oddly enough, despite the fact this is my longest section, rarely are there grammar writing issues for me. Grammar almost never. Writing sometimes. Organizations definitely go here. So if I find that the order was hard to read, But I will point out lots of things where the paper has got math problems or small math problems, things where the symbols aren't defined, all that kind of stuff, terminology that's not declared, all of that goes in here. And it also depends on how much I view the paper. So if the paper is sort of borderline, but I'm arguing for it to accept, I will write a lot. If the paper is bad, really, really bad, it has no hope, then I'm not going to waste my time fixing grammar in a paper that I believe will never be published, because I'm wasting my time, right? But if the paper, in my view, has hopes of being published, I want to help the authors along, then you want to give them lots of feedback. If the paper is really good, I can't find anything, well, then it might still be short. But my longest conference paper review was longer than the paper. Right? So I'm routinely writing, I will write reviews that are 6 to 8 pages long for an 8-page paper. That's just, so it's my style. So one of the things I dislike about open reviews is that I'm identifiable because I give them lots and lots of feedback. On the other hand, I've also won like 4 or 5 best reviewer awards because you really help people. Then the people who are deciding about papers actually think, oh, that's really good. Many conferences and journals will have a section for confidential comments. Okay, and this is really where you put things that would somehow disclose your identity, would be questioning ethics. It's not considered good style to directly accuse in your review somebody of plagiarism. Okay, you may feel that, but maybe they're plagiarizing themselves, which is not actually plagiarism, and you have no way of adjusting that. So one of the reasons to put comments like that in the confidential comments are they're always looked at by the PCs. If a paper has 5 rejects, the PCs may not look at stuff. If it's got 5 accepts, they may not look at stuff because it's pretty well decided. But they're definitely going to look at things you put in this section because that's what that section's for. These are comments directly to them. So things like, my group did this and we published it in some conference in that year, right? This is tricky. If I feel as a reviewer, work has already been done, especially that I know of because I did it, right? You write your review in this third-person, offset way, so you can say the paper should have compared against this paper from 1999 in this conference. Now, my recommendation is if, as a reviewer, that happens to you and it's your paper, don't cite just your paper because that's really obvious who it is. Cite 4 related papers that they should have compared to. And if you wrote a paper that they should have referred to, you must know some other ones they should have referred to as well. Chances are they didn't get them all. Right? So you can just add a couple that they're missing comparisons to. Other ones that are problematic, this is a double submission similar to paper number at conference, whatever the conference is. This is something where conferences have single review, they don't allow double submissions. The accountant reviewer is noticing this. The way papers get assigned to people, there's a good chance if I got a paper that's related to a paper at like BMVC and then I'm reviewing for CVPR, I'll get the related paper. Why? Because the papers are being assigned to me because I'm an expert in that area. That's sort of why they get there. So anytime you notice that, you make the comments, and even if it's only a 40% or 20% overlap, you make the comments, you let up the program committee members to figure out if they think it's a problem or not, right? It might be they feel it's not enough of an overlap, or maybe it does. It's up to them. And then I think the paper is plagiarizing paper and something, right? If it's copied large paragraphs, one of the papers I've recently had to deal with, my estimate was 65% of the paper was an exact copy of other papers. Okay. Most of it was the author's own work, in my view, but that still makes the paper unacceptable, right? I'm not going to publish a paper that 65% of it's already been published. That's just not, there's not enough new in it. But if you're doing this and you don't even know who the authors are, and I've had this happen before when I was a program chair, not as actually one I reviewed, but we had papers that were rip-offs of papers from other conferences submitted to our conference, not by the same authors. IEEE actually maintains a list of blacklisted authors. You do this, you're blacklisted for 5 years, right? Because that's pretty clear. Many of the major conferences and a number of the journals now actually have tools, just like, I forget to enable it. I will enable that for your next draft of your paper. I will run it through a plagiarism checker. One, so that you can sort of see what they do. But also just to let you know, right, we're going to be checking them for plagiarism because that's what all conferences and journals will be doing anyhow. And it's funny because sometimes you will have copied a sentence and you'll get like a plagiarism hit, right? Don't freak out. If your plagiarism score is 5%, right, don't worry about it, right? You can accidentally get 5% of your paper to have the same sentences and you don't have to worry about it, right? If you have a general description of here is the standard way people define the computer that we're going to have in a paper. It's going to be the same, right? Here's a standard definition of an SVM or a neural net or whatever. Right? They're very standard definitions. Yes, they're copied, but no one cares about that being copied, right? But if a major paragraph or two of your methods section is copied from a paper other than your own, that's probably a problem. Okay.
When it fits in the related works, like sometimes it's difficult to paraphrase what they're saying.
Yes. Yeah, so that will be up to the reviewer / editor to decide. So the general rule of thumb as an editor for me is if it's less than 10% and it's in related work or the introduction, we're not going to care about it. It's problematic if it's figures, because figures are, oddly enough, very aggressively checked by other people, but a sentence or two in related work is going to be fine. The best thing, though, is if you're actually copying something, quote it. Yeah.
What if you get some sentences and right after the sentence, because you did that on purpose, you did immediately the citation?
Right. So the proper style is if you are literally quoting them. If you take two sentences from them, then your style should be something where you actually use quotes and you say, as cite whatever said, and then you put it in quotes, right? As opposed to, here's exactly their words, and then just a quote after it. That's not a proper quote, right? So as an editor of a journal, I would tell people to rewrite that section, right, to properly attribute the words. If you just want to use a cite, then you should be paraphrasing, not quoting.
I mean, like, if you use a definition, this is according to this range of this field, and then you do.
Yeah, so if you're really doing, so as I said, if it's a standard definition, right, then yeah, that's okay, right? If it's, something more significant, then, quotes are just the proper way of doing it. So if you said, this quote, end quote, according to whatever, then you've been very clear that that was quoted. It's always safer to do it. Almost no one's going to say, that's a problem. You quoted 20% of your papers. Like, they're standard definitions, no one will worry about it. But again, at this level, it's pretty minor. I don't think you have to worry too much about it. But when you get wholesale paragraphs, and much to my chagrin, one of my students submitted a paper once where whole paragraphs of the paper we submitted with my name on it, he had copied from another paper. He was not happy when I found that out. And he just felt, well, that's what we did, right? He was a first-year PhD student and came from a place where in school they did lots of that. They just copied whole paragraphs of other people's things. He did have a citation at the end of the paragraph, but you don't copy that much and just put a name at the end and think it's right. But when English isn't your native language, it's a natural, easy thing to do, and we try and just fix that. So I will actually set it up. It's not set up now, but I will make your next draft so it will go through the Turnitin software, which is a weak but okay plagiarism checker, and give you some feedback on that.
What was the name of it?
Turnitin. Well, it's built into the Canvas system. So, and then in most conferences, they have some sort of scoring numbers. So I'm going to use the ones most common in my field. NIPS has 10, so these are just like guidelines. In generally, the two most important things are either bigger is better or smaller is better, and you got to figure that out, right? We like to use words because the numbers are ambiguous. So weak accept, which I'm not sure why I started with weak accept instead of strong accept, but it's similar in quality to the lower half of the accepted papers. So in our field, that would be something that's in the top 20% of all papers, because our acceptance rate's around 20%. If all accepted papers are 20%, so if I have 10 papers to read, I would expect 2 of them to have a weak accept or a strong accept if statistics apply. 10 is a small sample. You can get none, you can get 4, but it's okay. Strong accept, similar to the upper 50% of accepted papers, right? So if you think of all the accepted papers, strong and weak cover all of the accepted papers. Neutral, borderline. Some conferences, by the way, refuse to have this just because they want you to make a decision. That would be something in sort of bottom 10% of the accepted papers or the top 10% of the rejected papers. Weak reject, sort of the top half are rejected, but importantly, not fundamentally broken. I believe you should use the word strong reject to a paper that is so fundamentally flawed, it cannot be published no matter what else they think. And you would want to argue, here's why this paper has no business being published. Okay, if it's got theorems that are wrong, if it has experiments that are wrong and misleading, right? Those are absolute rejects. If the experiments are a little small and you think, gee, these aren't really convincing, that's not a strong reject. That's a weak reject because other people might have a different opinion about that, right? But if the experiments left off the top 2 algorithms in the world that they should have compared to, then it might be in the strong reject category because no one could draw a good conclusion because they didn't do a good comparison. Right? So as a reviewer, you want to make sure you really focusing on the big picture. Don't worry too much about the minor issues. It's very easy to find lots of these. And no one's going to be greatly impressed if you find 3 pages of lots of little things, right? So when I say I have these long reviews, it's not lots and lots of little things. It'll in fact be a sentence in a paragraph or a sentence or two, and then like half a paragraph about what's wrong with it and how to fix it, right? And then another sentence or two and a paragraph of what's wrong with it and how to fix it. So you go through lots of those. Really focus on the make or break issues. If X wasn't there, it would be a much worse paper. If X was done right, it would be a much better paper. Those kinds of things really help a reviewer. Be considerate of the space. Don't ask for something you think should be out of the paper unless you also talk about what's removed or make it shorter. Right? If you say, this is also a thing you need to understand when we're reviewing, right? If, as a writer, you write 6.5 pages and you were allowed 8, I, as a reviewer, will say, anything that's missing is something you haven't thought of and I will hold it against you. If you wrote 8 pages and you fill those up with all stuff that I can't say is irrelevant, then it's much harder for me to hold a lot of it against you because, well, it's a trade-off. You need to put this in but take that out is at least a reasonable choice. Whereas if you just left lots of blank space, that means you didn't even think about those things. Not like you made a hard choice, right? So if you're going to say you should add this to paper, it's really helpful to say this part of the paper is not that relevant. You can reduce that to make it smaller. So students often want to have examples for reviews. It's a good thing. I'm not going to give you, I will give you some of mine, but first you have to understand my papers, and then you can understand our reviews. My recommendation is talk to your advisor. Your advisor should have papers in your area, almost assuredly that have been rejected, but even if they haven't, they've had ones that have been accepted. You can get some balance of reviews to go with these papers. Chances are you wanted to read those papers anyhow, so ask them for their papers and reviews, and you'll be able to get some. There are a couple places where you can find open reviews. There's a place called openreview.net, which is a tool used by conferences that like to keep everything open. I'm not a big proponent of this for political reasons. Reviews can be used in ways that were not intended for the reviewing process, and I have seen them used that way, so I don't like to have them out there. NIPS is sort of interesting. NIPS is somewhere in the middle, in fact, in part because people argue the same way I do, that negative reviews about your paper being rejected can doom your paper forever and could hurt you at tenure or promotion time. NIPS publishes the reviews only of accepted papers. So if the paper's accepted, then there'll be the reviews and you're going to sort of see what's going on. So both of those give you some place if you're in the area, anything related to machine learning, you can find a paper there. You can find, for NIPS, I think it's the last 3 years, maybe 3 or so we've been doing it. Open Review is also about 3 years old in terms of work it does. So you can find examples. But the best place is to ask your advisor. You can even ask other people. I don't know if I've ever had it for a paper, but for proposals, I've had people from other universities ask me for my proposals and the reviews. And I routinely give them out, but not everyone will, but it doesn't hurt to ask. They can always say no. But if you're seeing a paper, this is another thing that's especially interesting. If you see a paper in archive, and some of you are citing stuff in archive, you want to dig down and find the final published version, it is sometimes very interesting to see the difference between the first version of an archive paper and the final version of the paper as it was published. And then, in fact, those people, you might write to them and say, it'd be interesting to see why your paper changed this much. Can you tell me a little bit about it? Do you have reviews or whatever? Very often, those papers change because they got reviews that said, here's what's wrong with your paper, here's how you're going to fix it. And then they move on and they make those changes in the paper. So we have long sequences of papers. First version, reviews, reject. Second version, review, reject. Third version, review, reject. Fourth version finally gets published. Right? So you go through trying to make the paper better. Sometimes it's the experiment, sometimes it's the story, sometimes it's a mixture of both, and you go through all of those. So, okay, so we're going to go ahead and take a break, be back by 10 of, and then we'll start on experimental computer science. By the way, these slides are uploaded. Both these and the next one we're going to do are uploaded on Blackboard or Canvas, whatever it is. Yeah.
So, I just noticed about what you said about the archive. I did my best to do that. What I found out about two particular papers was that they were either were published so recently.
Yeah, no, there's papers that only exist in archive, right? And there are papers that are old that only exist in archive.
One other thing, I found out that, for example, for mobile net, the first version for some reason didn't get accepted, but the mobile net V2 was published.
Okay, yeah, that's
So it's fine if in my server paper I have two of these archive papers
Yeah.
that haven't been published but are related to the next published version.
yeah. So as long as you sort of explain what's going on, right? So if the paper's old and it's not cited, then I would really question it. But if it's old and cited, it's fine. If it's new, it might not exist yet, so that's fine too.
Excuse me, sir. Can we cite rejected papers from that open view? Because some papers do.
So I would be very careful about citing them.
Okay.
So first, they're in archive because that's OpenView is based on using archive. But if the paper was rejected, you then have to ask, was it rejected for the right reasons, right? Because if it was really the paper was badly written, not that the underlying idea is broken, and you cite it and sort of say, well, it was rejected, therefore the idea is wrong, right? Then you're not being very honest about it, right? So you can just be very careful, right? So if your analysis, and this is why lots of people, including people at NIPS, right, are now sort of saying this OpenView's got lots of problems because people are doing exactly that. They're citing papers saying they were rejected and then using that as an argument in a paper that may or may not be. So now as a reviewer, I'd have to go look at these rejected papers and try and analyze, is that analysis right? And that's not also always appropriate. But if the paper was rejected and you learned something from it, right? Paper might have actually, so I mean, we have one paper on Open Review, the one and only one we'll probably ever have. But you know, the reviewers just didn't get some of it. And we argued. So there's like this whole discourse of my student arguing because he wanted to argue, and I said, fine, it's not going to make a difference, but go ahead and argue it. They will never admit when they're wrong. Not once it's public. That's the other odd part about it, right? Because it was public and they made a decision, they'll never change their mind, right? If it had been private, they might have been able to change their mind. It's like, yeah, that was probably wrong and we'll overrule them, but they don't want to publicly do that now. So it's despite their argument that this will make it more likely for everything to be fair, it's like, once it's political, it won't change.
Okay, I have another question.
Sure.
About, I'm working on the natural language field, and some papers have like examples like sentence or paragraph. Can I use their same examples?
Yes. You can always use examples, right?
Yeah.
The question is, how do you cite them, right? So if you quote their examples, or if you're using it in a figure and you're saying examples taken from, square bracket, whatever, that's fine.
Okay, if it's like figure, but it's like text.
If it's text, you can still say, using the example from whatever, right? But since you're trying to say exactly what the example is, you want it in quotes anyhow, right? You don't want to have it mixed in your paragraph. So it's perfectly fine to use their examples as quoted material.
Yeah, I used like 10 examples.
Italics? Okay,
from
yeah.
different.
Yeah, no, that's
So
perfectly
it's
fine.
okay.
Yeah.
It's not
No,
like figures, it's like pictures.
So even figures you can use with citation, especially in this survey paper. If you are really publishing it, the figure might require the publisher to get permission from the original publisher. Okay, so in my recommendation, what we normally do is we submit them with figures from somebody else, and then if accepted, we redraw them so we don't have to, and then we say adapted from, and we still cite them, but it's not exactly the same figure.
Okay, so it's okay if I say adapted from.
Oh yeah, yes, yeah.
Thank you very much.
When I was doing the previous assignment for the survey papers, just getting the browse and all that, I ran across one paper in the journal that I thought should have been looked at as 8 papers. That was one of the final ones I reviewed, and it was just, it had original stuff in it. Then I found in the same journal, there was one paper written by the same author, so it had been broken into 2 different ones, and I found the exact same thing. When you're a reviewer, how do you address that kind of thing when you're like, you're looking at going, way too much content, way too confusing, way too long?
That's pretty much part of your review. If the paper's too long. So most journals have recommend lengths, and so when you say it's too long,
I think this one actually went beyond the length that was
And then oddly enough, sometimes you'll have reviewers that say, I got 2 papers, they should combine into one. And the reason for that is while you may think it's too complex, like if there's one overarching theory that connects them, they might say it's better to have those 2 together instead of part 1 and part 2. That's a...
Well, and I guess I'm curious is, when you have too much content and you break it into 3, is that, would you prefer to publish them at different times or all together or in the same journal? Or does it get to a point where it's like, this is what you're publishing to?
So that one's, I don't have sufficient experience to answer from a personal view. And as an editor, I've never accepted more than 2 papers from the same authors in the same issue. And even that's pretty rare. Very often it'll be like, which one of these 2 is most important? I'll take this one and one of these over here.
That's kind of what I was wondering, because it seemed strange to me. I had 2 papers that had the exact same title, and I'm like, it's a little bit confusing.
Right, so the one issue I had, the papers were actually called something, 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 this case, something, 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 this other case. Right?
I think there was like one difference.
Generally, so what's funny is if one of them is introducing the core theory and the other's application, that I'm also seeing where it's sort of theory and application. But that's actually easier to combine into one paper. It's just when they have 2 very different applications that something different. That generally the authors, I would say the divided ones are the authors pushing so they can say they have 2 papers. I know in my cases, the times I've had it, we had once where it was recommended by reviewers, but in fact the recommendation was it gets split in 2 pieces. The first half is ready to go. The second half needs a lot more work. We're going to jettison it, they can do another paper on that, and that'll be a new paper, and it was a new paper like 3 or 4 months later.
And one other note, less positive note.
Canvas was doing some weird stuff yesterday. So I knew there was stuff due on the 7th, and I pulled it up, and I couldn't see anything turned on. So, I was able to catch up on Journal 5, but I couldn't do anything on Journal 6. So it's
Okay. Sounds good. Thanks. Actually, one more. So, when you're at a point, and this is kind of part of it, where you think that it might be beneficial to kind of change the structure, I think it's because it's more applicable to the differences you're trying to highlight. But you're already going down the path, and you're kind of you're working with another author, and you don't want to.
So I will discuss that broadly because you're actually not the only one who's had that question. Some had it in Journal 5, and I'll talk about that. So I'll just discuss that broadly. So it's not.
One more question. I feel like it's a challenge with when you want to have my pictures and the papers, and I know you commented on that because I saw it several ways, like having the pictures with the figures, but it doesn't look like it. Like
Pictures with the figures?
I mean, having the pictures that when I have in the paper, it just is stealing. It's stealing the because it's it's 2 columns, so it doesn't look like perfect. So it's fuzzy, and another one even for the table. I tried with the table just even if I want to do it one by one, I tried to do it with another tools. Also, there's another tool that's inserted with the Excel. I tried them all.
Okay, so those are good questions. I'll talk about those in general because many people struggle with the figure other issues. So.
Okay.
The most amount of papers are published by Dr. I was reviewing their history of publications, and he had the most publications
Most doesn't mean best, just. But I do publish a lot. But I mean, there's many faculty in the department that publish. But oddly enough, because I have the most money in the department, it's much easier for me to publish more than everyone else. Because if you have 10 PhD students and you expect them all to do a couple of papers, you get a lot of papers.
2 papers he had, the advanced. One of them is open access, open semantics. The other one is open access with ESL.
Yeah. So, but you're doing adversarial stuff though, right? Yeah. We only have a couple papers on that, but I'm happy to sit and chat about adversarial stuff sometime. Right? Unfortunately, my views are very cynical, but that's I actually, one of the talks I give includes the 12 things we thought cause adversarials that don't. Right? We don't know what causes them. We have no theory. No one has a theory of what causes them. And because of that, I also believe we have no theory about how deep learning actually works, because no current theory of deep learning suggests adversarials can exist. Right? So they're all I know so far is it's not any of this list. What else it is, I don't know. We got some ideas. We keep trying them. Come up with a hypothesis. We go out, we run an experiment, we test it, figure out where it's going. So, and you're doing it in natural language, where I don't have the intuition, but my guess is the things are related, but I'm not sure. Journal, you could publish this, right? So there's one survey that's recently been published on adversarials. I'd have to check where. The problem is, the only good journal that does just surveys that would include this is ACM Computing Surveys. It's very high level bar. It's very big. But see, I don't know NLP journals very well, but machine learning journals, right? The bar is reasonably high, but a survey for some of those might be acceptable. So something like, well, JMLR, no, they're very theoretical. The journal called Machine Learning, maybe. It's an Elsevier journal. It's not quite as good. Mid-tier journal. Well, so if you're doing adversarials in natural language, then it has to be related to either adversarials, machine learning, or natural language, right? It's really hard to do it in communications journals if you're not talking about communications, right? Okay, so before I get started on the next topic, there were a couple things which I forgot. I got to open the other window. Yesterday I went to read Journal 6 or whatever, and it told me there were none, and apparently a couple of you had issues submitting them. I know Mark did, right? I don't know what was going on with Canvas. I wrote to the Canvas support people. By the time they wrote back to me, said everything looks fine to me. I looked and it was fine, but it was now like 9 o'clock last night and I didn't read it anymore. So I in my other class, I just graded their stuff. So I did not give you feedback on Journal 6. I will try and get that done tonight into tomorrow, just so you can get feedback. It was also not that far after the last one, but.
If they have feedback but not grade from one of the journal, is it okay?
So if I forgot to grade something, I will eventually figure that out, or you can just tell me, right? So the system is particularly annoying depending on the order in which I type in comments or I type in scores. I have to hit the submit button and things in a different order. And so sometimes I wrote comments and you don't get them. And I don't even notice it because as far as I'm concerned, I wrote a comment. But as far as the system is concerned, I didn't hit the submit button for the comment. So, and after I've submitted a comment but not submitted it, right? So if I hit return, it submits it. But then there's a button that says submit this comment. Right? If I don't hit that, then it won't enter your score. That's its way of sort of prompting that I did something. But if I enter your score first, and then I do exactly the same thing, then you just never get the comment. So it's very weird. I haven't mastered Canvas yet. So anyway, a couple of things that came up, and I gave in your drafts. I gave many of you comments. There are many of you that had figures that were impossible for me to read. Right now, that doesn't mean you can't read them, but I'm a little bit older, and the bifocals, maybe there's a line where I could get them, but maybe not. In almost all the cases, I gave you the LaTeX command to have a double column figure, which is /begin figure star, right? Which will force the figure, and then of course end the same thing. That will make your figure 2 columns wide. It'll take the full width of a page. That way you can, if you have a figure that's got a lot of stuff in it, like many of your classification hierarchies, there's no easy way to do that, right? This will give it something. It'll float to the next page. So even if it's in the middle of the first column, it'll float forward to the next page. We'll try and put it at the top of the page. There's a couple of commands, If your figure is too big eventually, LaTeX will complain and like not be able to float it anywhere because it's bigger than a page. But this will give you something pretty big. In your figure commands, if you do this and the figure is bigger than a column but not really justified for a whole page, it'll look really bad. So in your include graphics command, you can set width equals 4 inches or width equals 5 inches, or whatever. You can set some command. So if you're not sure about a LaTeX command like that, you can just Google it. There's ways of making those figures look pretty good. If your figure is borrowed from somebody else's paper and cited, okay, be careful how you borrow it, because if you have it as a small piece of your screen and you somehow do a screen capture, which I'm pretty sure at least 2 of you had, because that's why even when I blow it up, I can't read it, right? It just doesn't have that much resolution, okay? You might try making it really big on your screen and then doing the screen capture, or use a tool that will read a PDF and turn it into a bitmap. So something like GIMP or Photoshop, either of those tools will read a PDF file and they'll convert it into an image. But you can do it so that it's a very high resolution and then crop out the pieces you want, depending on whatever tool you want. For the draft, I wasn't involved where I just wanted to give you that feedback that in the end, it's got to be readable. And then many of you had figure captions that were very different. So there are definitely styles. One of the journals that I read regularly does not allow more than a 3-line caption. It is one of their rules, right? They're like, you have to describe it in 3 lines. It's like, I'm sorry, right? I don't want to have to figure out where in the paragraph I have to read to be associated with that, but that's their style and process. My recommendation, and you've seen some of my sample papers, right? I have captions that are like a 1/4 page because I want the figure and the caption to be read together and to tell the story. And instead of having a lot of detail in the text describing the figure with a reference from the figure to the text, I do it the other way around. The text just simply refers to the figure, right, at that point in time, and it tells the entire story. Why do I prefer that option? Because when you scanned the paper, what did you read? You look at the figures and captions, right? So if you tell the story in the caption of the figure, they get it. If the figure caption says, right, a system example, I don't know what I'm supposed to get out of that. You got to tell me the story in the caption. So as I said, I like the storybook version, the comic book version. Figure and caption, I should get everything, right? I shouldn't have to read the text to figure out what's going on. Journals that have that attitude are because they actually don't want people skimming their articles. They want you to have to read. Right? I'm sorry, they can tell me that, but that just means I probably won't read their articles as much. But okay, so that was a comment. Some of you are struggling with your story still, okay? That's not necessarily terrible. You will, if you're working your process, that's okay. If you change your story, that's okay, right? If you're as you're reading, I was talking about this assignment with some other faculty who thought it was very odd that I had you try and write your categorization and tell your story before you read all the papers. They're like, should they have to read all the papers first? It's like, which ones, right? The whole point of this was to help you choose which papers to tell a story. On the other hand, as you're reading your story, reading your papers, you recognize your story isn't the best story, or isn't a good story, or isn't viable. You're allowed to change your story, right? I told you the story of that 2-page survey paper I did, right? The story that ended up in that paper is not at all. I worked on that paper for weeks, but I didn't find a story that worked for me. So I never actually started writing. I just kept thinking about it. It's like, so I didn't go through all that, but I had 3 or 4 other stories for that paper on open set stuff that I thought about, sketched out some ideas, and just decided they didn't work. So I wasn't going to bother writing that. So you're farther along, but you got to balance what's called the sunk cost fallacy. Okay, the sunk cost fallacy is a standard economic term that refers to the fact that you've put a lot of money into this. In this case, you've sunk a lot of time into where you're at. Okay, and so at a certain point, it is natural to say, I've got all this into it now. I'm not going to throw it away and start over. Okay, but we call it the sunk cost fallacy because that isn't actually a valid reason, right? What you really have to do is estimate how long will it take me to finish this version and will it be good enough versus how long would it take me to finish that version and be good enough, right? So while I had started that paper, and I actually had like 3 pages of that paper written in the first storyline. But on the third page, it just wasn't working. I just threw it all away, right? I started again from scratch. I didn't try and resave much because it just wasn't working. And the way I had written it, it was hard to try and reuse anything. So sometimes it's easier to start over. So ask yourself, given where we're at, or given where I'm at, what changes can we make? What's the cost of those changes, and what's the value of those changes? Don't worry about how much you spent on this one version. Worry about what do you have left to do and what are you going to accomplish. Okay? Now, given where you're at and the fact that this is a class and this is not the final version, right? You might be willing to say, and it's perfectly fine, it's good enough. Right? Okay? You will face this many times in your career as you're writing. Right? I've had papers where the day before it's due, we think of a much better way of doing it. The day before it's due is too late. It's not the sunk cost fallacy. It's the deadline is tomorrow, necessity. That's what we're doing, right? So just go ahead. So you can balance that in this class. You can say, yes, I've seen a better way. You can ignore my comments, by the way, right? So I'm not grading you on do you listen to me. I'm grading you on do you have a valid process, okay? Now, sometimes my comments are going to be really hard to ignore. If your story doesn't have enough complexity, if you have 7 papers in your citation list, right? I'm not going to ignore those, right? But if you tell a story that I don't like, but I can see its value, I may be fine with it, right? Many of you are telling stories that I don't like, but I don't care about that. I care about your process, right? And getting through to a valid paper. Then citations. And again, it was a draft, so I'm not going to worry about that. Many of you were citing things without complete citations. So when you run BibTech will complain, right? No journal name for this, no year for that, okay? When you get done, there shouldn't be too many of those such errors. Sometimes it'll complain like, right, no number for version, whatever, right? If you can't find it, but those errors are things that with a little bit of effort, you might be able to actually find those answers. Google Scholar, despite how it's great value for some of these things, is not the definitive reference for some citations. Lots of what Google Scholar has in it are crawled from websites where people don't bother to fix everything up. So one way of trying to fix your references is to take that partial reference you have, first in Google Scholar, look through. It'll often say like 1 of 16 versions. Look through the other versions. Oddly enough, they might have different BibTechs, right? Sometimes better BibTechs. Google has no way of knowing which one's right, so it just lists all 16 of them and lets you choose. So that's the quickest way. And if not, go to the original source. So if it's an IEEE, go to Explore. If it's an ACM, go to ACM, right? They will have the proper reference. Right? And if it's reasonably recent, you should be able to find those, right? And I'm not going to take off a lot now, but by the time you really want to submit something for a journal, you should know they're not going to be happy if they have all those things. Right? As a reviewer, it is actually a common comment for people to say, this paper has improper references, and they'll tell you mostly because they want them fixed. But if you have papers that I know exist as cited publications and you cited only the archive version, as a reviewer, that's a negative to me because it shows you're being really sloppy. You're not actually keeping up with what's going on. And if you're sloppy there, how much am I going to trust you other places? Right? Because you're just not being good about your work. So, okay. Any other questions about writing? So look through your go ahead, Bill.
I think you see it here in 2016. They said they had this chart up, and they said 90% of the reviews were done in the last 24 hours before the deadline.
So 90% of the reviews are submitted in the last 24 hours before the deadline. I can tell you that as a reviewer, that is almost always true of me. I rarely submit them before the day they're due. Right? I might start 2 weeks ahead of time, and then it's just a question of when do you upload them. It's especially true. So I do many of the reviewing sites have what they call online and offline reviewing. I have no idea who likes to sit and type into a form where you put stuff in a box and put stuff into a box and put stuff in a box. Maybe somebody does, but I do all my reviewing offline, and they actually have like an XML file. You edit the XML file and then you upload it. In fact, so if you do it that way, it's one XML file for everything. They've been trying to encourage us to like submit the ones you have done. Because if I start 2 weeks ahead of time, I may get 3 or 4 papers done, and then have a couple days where I do absolutely nothing, and then I could have submitted those 3 or 4. But Actually, I can't because the way the XML upload works, right? It will fail if the file already exists. So they haven't fixed the tool to make it any better. So I always wait till the last possible moment. Okay, so this week, for the remainder of today, I'm going to start on experimental design and computer science. I will not finish. Next week, Sung-Yun Ching, who does work on blockchain, whatever, he will be talking about his research. So we're going to start having guest faculty come in, and then in about 3 weeks, I'm going to ask you to start giving talks. We haven't talked about that yet, but we'll get to that. So first, we're going to have experimental design. Then I'll have a talk on giving talks, and then some of you will be asked to give talks. So if you are interested in volunteering to go earlier in the order, send me an email. We can put you in the list. You might be thinking you don't have any research. Well, you just did a survey paper. You could give a talk on a survey of law for whatever, right? That would be a reasonably good talk. So your talks, I'll be looking for a 15 to 20 minute talk. If you actually want to talk about your research, that will also be fine, because then you might get feedback on your actual research stuff. We'll see where that goes. But I do have some faculty that will be coming in, so we'll be working around their schedule about them giving you talks about what is research in different areas. And then I guess, actually before you guys talk, I was going to do the cloud computing talk. So we have like, I guess 4 weeks, 3 weeks, 4 weeks before you guys would start talking again. Okay, so experimental design and computer science. So part of this is actually experimental design, and part of this is experimental design and computer science. So experimental design is really important. So computer science as a field really has its origins in mathematics, engineering, and some commercial practice. And if you look at those 3 different origins, they actually go into different branches or subsets of what we call computer science, which is the theoretical computer science, experimental computer science, and design or applications-oriented aspects of computer science. Right? So depending on where we're trying to both start from and where we want to end up, we have different styles of doing it. And we really want to balance and synthesize these aspects. So from a mathematics point of view, we're looking at things like, what is it? How do we prove something? CS is far more about how do we do something, although there's theoretical computer science that just has proofs. And so from a theoretical point of view, why might I need experiments? Even if my paper has theories. Why do I need experiments? Sorry. Validate the theories, right? Well, so I already proved them. So why do I need to validate them? I proved them. I have a proof. Well, but if the proof is a valid proof, right, it's a proof. Why do I need experiments?
Maybe we should go back to that quantitative analysis you were talking about earlier.
Well, I mean, so experiments are a type of quantitative analysis, right? But this is, I'm being the devil's advocate, but why would I have to?
Isn't that why they have the CERN fighter in Switzerland is to verify their work?
Well, so that's actually in the theoretical physicist versus an experimental physicist. So with respect to the quantum mechanics that underlies those particles, right? There's a theory that says this should happen, but there's no proof. In mathematics, right, I can have a theorem and a proof, right? So I can prove that, right, there are infinitely many primes, right? There's a proof of that, right? Do I experimentally need to go out and validate that there are infinitely many primes? Probably not, since I will never finish that experiment. But there are things for which we have proof. So, but in my view, almost every paper that has a proof needs an experiment. And I'm just trying to get you to think about why I might feel that way, but why might it need it?
For example, when at the first convolution and neural networks were developed, you had a proof that they worked, but they couldn't test them because computers were not fast enough. So how do you know that they work?
That's why we have a proof.
Yeah, but you know that the proof says something that you cannot actually do experiments on.
Okay, so you could be worried that the proof isn't true. Okay, Claudia?
Well, as far as working batteries or with controls and stuff, that physical systems sometimes reflect what the
Right, so that's the real reason. Theories make assumptions about the world, and they say, assuming blah and blah and blah and blah, then this follows. Okay? The real question for experiments is not does this follow given these assumptions? The real question is, do those assumptions come close to modeling the real world? Right? If I have something that I can prove is true, but experimentally is terrible, right? Is it a good algorithm? Probably not. Okay. Early in my career, one of my early papers was titled something along the lines of, "I don't care if it's optimal. Is it good?" Right? I worked in a field where we did lots of optimal algorithms, many of which were optimal. We could prove they are the best possible algorithm, and then you would implement them, and they were terrible. Right? So they were the best possible algorithms given a set of assumptions, but those assumptions didn't relate to our world. Right? So in fact, the good thing, the whole point of that paper was, if an algorithm is optimal and not good, you have learned that it is a bad model of the world. Okay? If the algorithm is not good and it has no theoretical properties, you just learn it's not a good algorithm. Not that it's not a model of the world. The model might be fine, the algorithm is just terrible. Right? So you got to balance that. So.
I was going to ask, could it also be because we want to actually discover something new or a new problem that we didn't know exists? For example, in RNN case, the theory is that the RNN should be able to predict through multiple steps backward. But in practice, it can only predict up to 2 or 3.
In fact, what you're describing, which is also the CERN example, right? We want to separate the difference between theories in spaces that have, here's our theory, but we have no proof, and mathematics, where you have a theorem and a proof. Okay, in mathematics, there'd be a proof that it does this, right? So, but then the real question is that proof. So the vanishing gradient problem is something for which you can prove the gradients will get smaller. Okay, so that's a problem for which we know there's a theoretical thing. So, when you have your theoretical advance, right, you prove a theorem. It's fun for some people. It's short, and there's really no arguments. That's really not our concern because it's rarely enough, right? The experimental stuff is this real? Does it really work? Right? So if you're really off, and Ryan's not here today, but if you're off proving weird things about graphs, okay, so Ryan's paper is looking at graphs for driving, right? So like Uber, right? How do we have the algorithm to allocate drivers to clients in Uber? That's an interesting problem, okay? And a number of people in the space worry about provably optimal algorithms, okay? But, at a certain level, the algorithm is provably NP hard, okay? So, for n equals 100, maybe you can afford to solve it. For n equals the size of Uber, it's useless to worry about whether or not your algorithm is optimal, right? It's a question of how there's some balance of things. So finding that balance is really important. And that's really what the rest of this talk is about, which is, right, dealing with that. So it doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the experiments, it's wrong. Okay, that's a physicist's view of theory, right? So Feynman was more of an experimentalist, but he had some good theories as well, right? In my view, it doesn't matter if it's optimal unless it's at least good in real experiments. So you got to have those things being out there. On the other hand, there's lots of paper, conferences and journals for which the mathiness of having a proof might significantly improve your paper's chance of getting accepted. So there's time where you want to have that formalism and be able to prove it, but also then relate it back to, is it good? Does it actually have good results?
So sometimes it's very, very hard to even thinking about a mathematical proof, even thinking about how do I do this? But let's say that the set, the universe that we are working with is finite in a reasonable size. So if you do an experiment and you show through the experiment that what you say is true, does the experiment waive you from finding these mathematical proofs?
I would say the majority of computer science papers, probably 95%, hope to be in that category where the experiments show their results without having a proof. So yes, the majority of computer science is driven by experimental analysis, not by proofs. Okay? The effort it would take to sometimes do the proof might be impractical. But even if that is not the problem, you have lots of things for which you can't prove it because the inputs are unpredictable, right? If your input has human input, the outputs might have a lot of variation and there's no way to prove things, right? On the other hand, you might be able to abstract away some part of it and have proofs, right? And so, to be honest, during your PhD, depending on who your advisor is and where you go, right, that might be part of what you try and learn is how do I abstract away a mathematical model to explain it? As I said earlier, right, you want to be able to explain why it works, right? We have multiple theories that we've developed in our lab after we've seen the experiments, right? Actually, the experiments give you insights into what you may or may not be able to prove or do about it, right? You look at them, you say, oh, well, maybe this is the case, maybe that's the case, right? You have a hypothesis, now you can run some more experiments. You can also maybe develop a model of it and come up with that. Lots of computer science definitely has that category where there's no proofs. So what is an experiment in computer science or experimental computer science? And it's the creation of or the experimentation with or on non-trivial hardware and software systems. Okay, so taken broadly, these systems are really the computational artifacts that people talk about. These are not just an algorithm, but it's really a systems level view. It can be just an algorithm if you're going to argue this algorithm is true across many platforms, or it could be completely a systems level view, which is I need all of these parts working together. The more complicated the system, the harder it is going to be to design an experiment. We will talk about that. But so the real idealized scientific process is form a hypothesis, construct a model, make a prediction, design an experiment and collect data, and analyze the results. Unfortunately, it doesn't normally work that way, but that's the ideal process. The real way it works is some mixture of these, right? Form a hypothesis, construct a model, make predictions, design an experiment, collect data, construct a revised model, make new predictions, collect new data, iterate a couple times until you get where you want to be. And sometimes it's build something, run an experiment, hypothesize a model, fit it to your data, and write a paper, right? Where the model comes completely last, right? That's really not the best way, but it gets you the math you need in some papers, and it will happen. You want to be on the lookout for when that happens. Ideally, the minimum step is if you do that, after I've built the model from my data, go test it on one more experiment to sort of show that it actually holds, right? As opposed to just being stuck with it. So first I want to start with dealing with reasons not to do experiments. This department is not that bad. Where I first started at Columbia and then at Lehigh, we had a number of faculty that were far more theoretical and felt they didn't need to do experiments. So I want to make sure we get through that just in case we get any of that. And then we'll talk about how to do experimental computer science. So oddly enough, at one end, there are people like Rod Brooks, the author of There Is No Silver Bullet and Mythical Man Month and a bunch of other stuff, really big in software engineering, that computer science is not a science, it's a synthetic and engineering discipline. So our phenomenons are manufactured, it's a type of engineering. So experimentation is misplaced. It is simply enough to build good things and they work. Okay, but other sciences are actually largely study manufactured things. So in physics, things like super heavy elements, lasers, right? These are all manufactured things. They don't actually exist, but we can still study them and understand their behaviors. And more importantly, we can make inferences about models. So the better our models, right, in terms of experiments and validating whether or not those predictions are useful, means we have to have experiments to validate those predictions. So if I'm going to tell you this is a better way of doing software engineering, I want to be able to run an experiment and validate that it's a better way, not just make a claim that, see, it's intuitive, that makes sense. So it doesn't just be theory about why we should do it. Experiments can't really prove anything. They can disprove things, so they can prove something is not true, but they can't really prove anything with absolute certainty. But they're good for reducing our uncertainty about theories, leading to new insights and whole new areas of investigation, quickly eliminating fruitless approaches, and testing theoretical assumptions about the world. I will tell you that in my lab, most of our proofs are done after some basic experiments to show that the idea works. I rarely have a theory, then build the experiment. I'll have a hypothesis, and then I'll go build some experiments, and then we'll try and deal with the actual theory part.
So there's things that says experiments cannot prove anything. So most of the papers do experiments and compare their own model with other models, say that the other previous work, something like that, and say that, okay, based on this experiment, our model is this amount faster, or this percentage faster. So this is an experiment that they're claiming, they're stating because they want to prove that they're better. So why do you say experiments cannot prove anything?
So with absolute certainty. right? We can show that we are statistically faster, right? Statistically better. That was last week's lecture, right? So statistically better doesn't mean I'm actually better. It means with high probability, I am better, okay? And realistically, it means with high probability on this set of data, I am better. On another set of data, may not be better, right? So that's so. But that doesn't. So experiments are really good because they allow you to actually draw a lot of conclusions, especially if you do them well. So there's a fallacy that was put out that people think computer science isn't a science. Traditional scientific method really isn't applicable. The subject of inquiry is information, unlike traditional studies that study things like matter, energy, the plants that exist or whatever. So, asking the question, is object-oriented programming, is it generally better, right? Is that really studying nature, or is it studying one human artifact, functional programming or procedural programming versus object-oriented programming, right? And the answer is not necessarily conclusive. On the other hand, if I take 1,000 people, I break them up and I do a proper study, I might answer whether or not those people produce better or more efficient code or whatever. So it depends on how I rephrase it. So if the question is object-oriented programming generally better? The answer is no experiment can answer that, right? But if I refine it, I might be able to answer a more refined question. So we really want to understand information processes. Computer scientists have to observe phenomena, formulate explanations, and test them. And that is the scientific method. It's the scientific method about things. In fact, physics, despite the fact that we talk about physics as a hard science, lots of physics, especially in the quantum space, is all about mathematical models of what we think might be true. Right? And then you go out and build some things and sort of measure it and interpret those and sort of see, they sort of are. Stephen Hawking's most famous physics results are about the information content on the perimeter of a black hole, right? It's actually literally about information. So it's not that scientific method isn't applicable. It's about how we process information, and then we can still build experiments to test those things out. This is another classic one. Current levels of experimentation are enough. Our experiments are big enough, we're already doing this. And in the late 90s, study of CS papers requiring empirical backup, 40-50% of them had none. No experiments were run in those papers, compared to less than 15% in non-CS papers, right? We're a young discipline, so that number, by the way, hasn't gotten much better. The last time I saw a version of this, I think it was a 2006 study, and we were up to 60% of our papers had some level of experimentation, okay? Now, most of our papers will have some demos, and we'll come back to that, right? But that's not really enough to do it, right? If other sciences and things that you might not even worry about as a science, like anthropology, right? You're not going to publish an anthropology paper without statistical analysis and data analysis that most CS papers wouldn't go through. So we can be much better about this. Experiments cost too much. This is real. They are expensive. They take both time, money, and actual energy resources. But you can explore cheaper options in designing experiments. But experiments are important. If you can narrow your experiment, you can make it cheaper. So this is an answer. You might not be able to afford your experiment. There's lots of times when I've decided I can't run that experiment because it's too expensive. It would literally take a year to compute, okay? Wrong experiment, find another one, right? That might be the one I really want to do. And maybe in 3 years I'll be able to afford that, but right now I can't. So you figure out how to balance out the things that you can get done. Lots of people argue demonstration will suffice. This is, in fact, I think the biggest problem in computer science. A paper to me is a demo. If they run it on something so small they can't collect statistics, then they have a demonstration, right? So if they have, I ran my program on this one set of data and I compared it to 4 other algorithms, to me that's not an experiment. That is a demo. Why? Because you can't collect statistics on that one. Maybe it's a huge data set you could, but generally people just have one number in the paper and show my number is better than their number. That's not statistically valid, right? It's not. That's what we talked about last week. So they can't really provide solid evidence, right? And way easier to hide some bias in a demo. If I carefully choose the data, that one demo might make me look really good, right? And literally it can be, if I start with the right random seed, I'm 20% better. If I choose a different random seed, I'm 20% worse. I will find a C that makes me look good, and that's all I'm going to report. And I guarantee there are papers you will see that have that characteristic hiding underneath them, and you can't tell because they only have one run of their program. Right? If you don't run it, if there's any randomness at all, and almost the whole world is full of it, you can't tell what's going on. So it's tricky. On the other hand, I like live demos. Right? They're not a proof, but if you can make it robust enough that it'll run and I can mess with it, then I'm going to feel it's pretty good, right? I mean, because I'll try random stuff thrown at it. This is another classic concern for why people don't want to do computer science experiments, especially in some of the software areas. There's just too many variables, and they're affected or swamped by the noise. Okay, so this becomes tricky. If I have a lot of variation, then it takes a really large experiment to get rid of the noise and deal with it. We'll talk a little bit about this. So this is actually where the answer to this one is you haven't thought through your experimental design. You want to come up with a design that allows you to reduce the variance and allow you to get through those effects swamped by noise. But that might often mean doing what we call a pilot experiment to analyze where's the noise, where's the data, the variance in the data, what can you do, and then designing the right experiment to get around it. Okay? And using the right statistical controls from medicine, psychology, or whatever can really help with computer science experiments that involve people. Because guess what psychology and medicine have to deal with all the time? People, right? If we have people, we want to borrow some of those. People argue that experimentation will slow progress, that it takes too long to do these kinds of things. There's some truth to that because if I take an experiment that's going to take me a month, I can't publish my paper until I'm done that experiment. On the other hand, good experiments will actually weed out questionable ideas and their offshoots. You'll get these hypotheses, and we see a lot of it now in neural nets where these things just pop up, right? And they don't have sufficient experimentation. And a bunch of people will chase after them for a little while only to find out they're really not very viable. The number of things that you start doing them, you experiment with them, you find out they don't really work. They work in a very narrow field of view. We have a data set called NIST, which is like the digits 0 through 9, right? And they're pretty much black and white. And we have lots of things that hold true for the MNIST data set that don't work for any other data set we can find, right? So that experiment, even if it was statistics, right, that's not necessarily a good representation of the world. So doing better experiments might allow us to actually build work faster. This one's tricky. It's especially true for people in fields where the sub-areas are changing too fast. So technology changes too fast. By the time I've run an experiment, the results are no longer interesting because they've been surpassed by somebody else. Well, that might be true. But if that's true, then your results weren't very interesting to begin with because they were already outdated by the time you finished them, right? So it might be important to look at more fundamental, long-term problems rather than just the quick thing I can try and get out and publish it. So if doing good experiments means the work has to be better before it gets published because it's still valuable by the time you finish the experiment, it might actually be good for the field to have to go down that path. So fallacy number 8, in terms of theoretical computer science, there are substitutes for it. Theory, well, as we already said, theory can be contradicted in practice because you had incorrect assumptions about the world. Right? If I assumed the world had only spherical chickens, inspecting chickens would be easy. Right? But chickens have wings and whatever, right? And oddly enough, if you actually try to inspect them for using UV light or whatever, looking for salmonella and whatever, it's rarely on the chicken breast, right? It's normally like under the legs or under the wings, the things you can't see, right? Why? Because it's also the things you can't clean as easily. So there's actually a correlation. You got to put the two together. So you can't get away with lots of assumptions. Intuition will often fail in the face of counter 200 volts. In fact, very often the most interesting papers are those for which the intuition is exactly the opposite. Adversarial images that we have some people looking at, right? They're intriguing, as the title of the original paper about them was because no theory for deep networks suggests they exist, and yet they do. And so the intuition of why we don't need to experiment and look at these things sort of went out the window. People were doing experiments and no one even thought of this sort of problem. For example, productivity is not necessarily improved by type checking. In the fields of language, there are people that have argued that type checking is really important and it will improve productivity, and other people argue it will not improve productivity. And the answer is, it depends. I guarantee type checking improves my productivity, because the time it will take me to find typos in Python code that have involve variables that don't actually exist, right, is very large. So I want the type checking to say, no, you can't do that. But for other people, that may not be the case. So it's a balance. You have to figure out where the experiments show things out. Science has to also be backed up by evidence. So you can't just have experts claim this is true. So we don't have to get too much into that. So, okay, so now we're going to jump into how we do experimental computer science, or at least the first part of this. So ideally, people like to think of, here is what research looks like. We have some computer, we have a controller, we build a prototype, we collect some data affected by the controller, we have some data acquisition. That's sort of what we like to think our system looks like. Really, it generally looks like that. If you've ever been in my lab, right, that really is a pretty good depiction of the back room. Things are just all over the place. By the time you start running experiments, all of a sudden in the middle of it you say, oh, I need to do this. You add some more augmentation. Oh, I need to do this. You rarely get to have the nice, clean, pristine outline of what goes on. So we like to think of the scientific method as we observe a natural phenomenon, we formulate a hypothesis, we test the hypothesis with rigorous experiments, modify the hypothesis, and then establish the theory. The actual method more commonly used is to make up a theory based on what you think the funding agent or the journal or whatever is looking for. Given that that's true, you then design an experiment to prove or to suggest, because you can't prove, but to suggest the theory is true. You publish a paper, rename theory a hypothesis, pretend you use the scientific method, and you keep modifying the theory or process until you actually get something that works. There are many times when our funding agents have said, go do long-range face recognition. Right? And oddly enough, when we started our project, we were told we could not use deep networks. So we had all these hypotheses why deep networks would not work and why this would be better. Within 2 years, everyone in the program was now doing deep networks, and we stopped doing everything else because the experiments were showing us otherwise. So then we had theories why deep networks were better. So you defend the process. So this is PhD comics, right? So this is a little bit tongue-in-cheek, but there will definitely be times when your advisor or your funding agent will have a theory, and you're going to try and design experiments based on that theory. Okay, and then you're going to try and support the theory. Okay, that is not the goal of good experimental computer science. It is not to design an experiment that will support your theory. The goal is to design an experiment that will test your theory. Okay, and you want to understand the difference. You want an experiment where if the theory is not true, you will get a result that says it's not true. We call that falsifiability, which really underlies the core of science. If you design an experiment which cannot falsify your theory, then there's no point in running the experiment, except maybe to get funding. So really, your experimental hypothesis. Now, this is the important, your hypothesis should really be plural, your experimental hypotheses, because you're going to go through many of these. But any hypothesis should state hypothesis that provide evidence for or against it and conclude whether it is supported or refuted. Okay? It should be precise, explicit statement, and falsifiable. If your hypothesis is, yeah, this will generally be better, okay, that's not yet a hypothesis. It's not explicit, it's not testable, it's not falsifiable, right? Because I don't know what general is, and I don't know what better is, right? So you wanted to refine your process down to something to be a little bit better. Along that way, you might say, I'm going to use only data that's specific to my problem, and that's perfectly fine, right? So you might choose an experimental data set to make your funding agent or whatever happy, or you might choose one that's convenient, right? But your theory should be more general than that particular data set, and you should be able to write it very explicitly. You then want to run an experiment to confirm or refute that. Ensure that the experiment really tests the hypothesis in a meaningful way, and then you want to be able to go back and analyze that. And I say hypotheses because along the way, when you run the experiment, if it refutes it, you often want to go back and revise it. Now I have a new theory or new hypothesis. I can change it. I can run the experiments again. You want to be a little careful about designing the experiment to make sure that you're not overfitting on your hypothesis based on your one set of data. And you also want to make sure that you've designed your experiment in a way that is reasonable and fair. Right? So here we have Professor Zatnisky. Sorry, I did not know it had funny noises. Right, prove that the squid is more intelligent than the house cat when posed with puzzles under similar conditions. Okay, it might actually be a good proof of that statement that when underwater, squids are better than cats, right? But that's not what, if then you make that into the headline, scientists prove squids are more intelligent than cats, right? Leaves out the conditions, right? Not very appropriate. And similarly, it's easy to prove that a cat is, smarter than a squid if we do it on dry land, right? One dies, the other. So you got to figure out what those environments are and make sure they're meaningful. But that's not our goal. But if you were funded by NOAA, that might be your outcome. If you're funding by somebody else, you might want the cats to win. So let's talk about your hypothesis before we get into the designing the experiment. Okay. So hypothesis might be that some system theory technique parameter P is good for task X. Is that a good hypothesis or not? Define good. So yeah, part of the problem is I haven't defined good. Assuming I define good, right? So, right, I have some definition of good. Is the rest of it a good hypothesis? It's an okay hypothesis if I've carefully defined good, right? So better hypothesis would be it's better than rivals Q and R for task X, right? One, it's easier to define better, and two, I've now put it in context. So let's say I define good as it has more than 25% efficiency, okay? And other algorithms have 90% efficiency. Well, yeah, it might be good because at some definition of good it was acceptable. The others might be a whole lot better. On the other hand, I might be able to change my dimensions and say, okay, good means it's at least 25% efficient and I can manufacture it for under $1, right? Where the ones that are 90% efficient cost me $100,000. The cost savings, right, might be, so when we talk about good or better, we generally want to stick to better. By the way, better is much easier to do statistical tests for. If you think about what we did with t-tests or whatever, right? Better is easily measured. Good is some fuzzy number. According to things like behavior, coverage, efficiency, cost, any one of those would be things we can make the definition of better for. And a classic way of designing experiments is to hold some dimensions relatively fixed or in some range, and then vary some others so you can actually show that it's better as you vary those. And we'll come back to that. So we were talking about evidence can be theoretical, experimental, based, or both. So often you want the things you don't vary in your experiments, you want to have a theory that sort of says why they're okay. Right? So if we don't have experimental variation about those, but we know that the algorithms are running on a computer and they finished in a day, that might be enough suggestion of cost efficiency, right? As opposed to they need a supercomputer and they finish in a month, even if I don't vary those dimensions. So when we're designing an experiment, we want to have a specification that needs to be complete and explicit about this is the experiment. This is a place where lots of students run into problems. They like to think of experimentation and experiment as the same thing. Going out and experimenting, where I'm just trying out some ideas, is not running an experiment. Experimenting might be helpful to design an experiment, but an experiment should be complete and explicit and sort of say, here's everything that's going to happen. You want to make sure the experiment really tests the hypothesis. You want to have a plan for managing variance. We will talk a lot about variance in the rest of this class, and definitely the next time we finish the experimental stuff, right? We talked about variance from a statistical point of view. If I want to draw a conclusion about one thing being better than another, the variance is what's going to drive my ability to answer that question. So if I don't control it, then I may not be able to answer my question. I might get a type 2. I reject a hypothesis I should not have because I don't have it. So designing experiments to manage variance is an important part of what we'll talk about. So we have to worry about controls, that other factors that have to be kept constant. We want to be quantitative. We want to provide numbers so we can run statistics over them. And we have to think about the coverage of this experiment in terms of, are the tests representative of the full range of hypotheses? And if they're not, we can always change the hypothesis and narrow it. So if I'm making a statement about data sets and it's true for images that are almost black and white, I can have one hypothesis. If I want to talk about all images, I need a broader hypothesis. So if I start with something broad, my experiments don't want me to conclude that. I can always narrow my hypothesis as part of the iteration process. But when you're designing an experiment, You don't want to come back and define these things after you're done your measurements. Because if you've done it after you've done your measurements, you're fitting to the experimental data. That's not a good experimental hypothesis. If you do that, you should go back and run one more experiment completely consistent with your current hypothesis, but not from your original data. So we're then going to talk about analyzing and reporting your results. So you're going to analyze this, look at the statistical evidence. Does it really support or refute the hypothesis? Make sure, which is really looking to make sure the differences are not due to chance or natural variability, which means you have to account for and quantify what those variabilities are going to be. You want to be careful. It's better to admit the flaws in your methodology than to try and hide them. If you submit a paper and the reviewers decide you are hiding flaws in your experiments, your paper has lost its credibility. And as soon as reviewers don't trust you, they don't trust you. If I don't trust you about this, why should I trust you about anything else? So if you present an experiment as solid and I see flaws in it, I don't trust your results because I don't know what else you're hiding from me, right? So I want to be very careful. You want to be careful not to generalize without adequate support. So you want to say, here's what we can conclude. Now, you can talk about a broader applicability as future work, right? You know, this might apply to a much broader class of problems, which is future work. That's okay. That's not generalizing. But to say, this shows we've solved this broad class of problems when you haven't would be too much. You can do a little bit of storytelling where you talk about some things and leave readers to conclude things that are a little bit vague. You can play a little bit with that, but don't go too far down the overclaiming side. And I will tell you, this is my style. There are definitely people out there that go the opposite. They overclaim like crazy, right? And they figure out they hit 70% of what they claim, that's good enough. Some of those people are really successful. So I can't tell you don't do it because you won't be successful. I just don't know how to be successful doing that. So I'm telling you my approach to doing that, which is to be careful and don't overgeneralize. Report everything, procedure, results, conclusions. You got to be a little careful. You don't have space in most conference papers to report everything. In your thesis, you can. You can really talk about lots of stuff. And we'll talk about this when we talk about running experiments. You actually want to collect a lot of stuff. I've run multiple experiments where things I didn't think were going to be important turned out to be the critical item in why people made their decisions. So think more generally, especially if you work with people, about how you're going to collect data to understand why things happened and why they didn't. Because sometimes it's not what you think that makes them then drive the decisions. And then you're going to try and prove your claims, which means you have claims to prove, right? And evidence to back them up. And evidence is convincing statistically significant numbers from well-constructed, where you're considered all influences experiments that are discussed and from which a series of conclusions can be drawn. So this is not quite the standard, but you'll notice that this hits lots of the elements of a good story because we talk about the problem, we talk about some details, we have to overcome some things, the problem, so we have to get statistical significance, so it's going to overcome the difficulties to reach some conclusion where we have our final result. So oddly enough, that story thing, and I know some of you are still struggling with telling a story, go back and look at that if you're really struggling with it. Telling a story is not fanciful. We don't need Goldilocks to show up in your paper, right? We need overcoming the obstacles and making decisions and whatever to show up in your experiments, and that'll sort of work. We go to 7:20, right? Okay, so we have time for the next piece of this. So this is a really good book. It's unfortunately both dated and a little bit specific to my field, which is empirical methods for artificial intelligence, but it's actually a pretty good book overall. And we're going to start with some of the material that comes from that, and oddly enough, it won't even sound like AI. I tried not to go too far down the AI, so we chose examples that come from his book, but are more general computer science. So evaluation begins with claims. So, and oddly enough, lots of people ignore this. But the most important, most immediate, and often most neglected part of an evaluation plan is making sure you understand what you want to claim. If I want to have a statistical test to show something, I want to claim on that. So X is bigger, faster, stronger than Y, measured somehow, right? X varies linearly with Y in some range we care about. X and Y agree on most test items. It doesn't matter who uses the system. There's no effects of subjects. That's a really hard one. It doesn't have, subjects have little effect would be a much better way of saying it as opposed to there's none. My algorithm scales better than yours. Relationship between size and runtime or whatever, right? Those kinds of things. A non-claim, which is really common, I built it and it runs fine on some test data. Okay, that's not a claim. Okay, slightly better, I built it and it runs better than X, Y, and Z on this test data is a claim. Right? But I built it and it runs okay on some test data. That's not a claim. Unfortunately, I'll bet every one of you has at least one paper in your survey right now that you would put in that category. Agree? Right? You've got a paper, that's pretty much what they did. They built it and they tell you about it. Okay? That's not experimentation. Probably have many papers, but let's see. So let's say we wanted to compare two algorithms. And this is scheduling processors on a ring network where jobs are spawned as binary trees. So not very AI-ish, right? So we have two kinds of algorithms. COSO, keep one and send one to my neighbor, left to right, arbitrarily. And COSO star, keep one and send one to my least heavily loaded neighbor. Right? So I'm just going to know the load of the processor to the left of me, the load of the processor to the right of me, and whenever I have a job to do, I'm going to do something and send one either left or right randomly, or send one left or right to the process that has least work, right? So if you did a theoretical analysis, you can look at this from a tree point of view, and you can look at this sort of for unbalanced trees and other conditions. It was necessary to want to test these two algorithms empirically, right? So one of them is really trying to balance the load to the left of me and to the right of me, right? If the load of the left of me is higher, then I'm going to give the work to the person to the right of me, okay? Sounds intuitively, so intuitively, do we need to run experiments to prove this is better? No, this is just obvious. Well, maybe we should, because we're talking about things that are random. So the hypothesis or claim here is that the keep one, send one randomly takes longer than COSO because COSO balances the load better. Okay, and notice the hypothesis has this important italics word, because. Okay, our hypothesis is not just that COSO takes longer than COSO star. That could be a hypothesis, but a much better one is about the causality. And then we want to have this because this indicates a hypothesis about why it works. Because otherwise it's really just this sort of beauty comparison. One's a little bit better than the other. Now, it's also helpful because if I can say why something is better, then I actually have in my hypothesis something I can test that might actually make the experiment easier to validate or invalidate. Oddly enough, it might be that COSO takes longer than COSO star, not because it balances better, okay? But we won't know that if we don't test that hypothesis. So the intuition is this is better at balancing, so let's make that work out. So in experimental design, we can then talk about what are our independent variables. That is the variables we control. Oddly enough, that's almost the opposite of independent, right? Independent are those things we control. The dependent ones are the ones we don't control. But you usually got to think of it from a slightly different point of view. The independent ones are the ones that can be varied independently. The dependent ones follow from the independent ones. They're tied to them. We have no direct way of influencing them. So if you get a knob, it's an independent variable. If when you tweak this knob, some other variable that you're not connected to changes, that's a dependent variable. Make sense? We want to make sure people get that. So we talk about these in dependency diagrams. Independent variables are the ones where I have some functional control over. Those affect these variables that affect a dependent variable. So what are the kinds of things I could have as independent variables for the experiment we're talking about for this ring? Independent variables. And so we have this ring. What are the kinds of things I control? Number of processors on the ring. Okay, that's one. What else? Somebody else. What's another independent variable? Right, so sort of here's the thing. So what else? The flow. Well, so we have two different algorithms. One says keep it, randomly assign it. The other says measure the neighbor's load and send it. So that flow is pretty much defined. The load, right? So yes, we can change how often a new processes spawn, right? That drives what is the effective load on the network. Anything else I might be able to? So depending on how we look at it, there are a whole bunch of other variables like how much memory do they have? What's the latency? There's a whole bunch of other variables you may or may not want to control or say they're independent variables, right? So we can fix them. So, so if we do this, and we do it with simple stuff where we just dump a bunch of processes, the mean time to compute jobs for the COSO algorithm, the dumb algorithm, is 285.25, and COSO star, the load balancing algorithm, is 29.35. So COSO is 4% faster than COSO star. Okay. Now this difference is not significantly different, most likely. Right. We'll talk about that in a little bit, but assuming that it's not, we didn't give you enough data to decide that. But assuming it's not, what happened? Why? We started off intuitively, COSO star should be better than COSO. Okay. This is why experimental compliance science is good. Right. We had a hypothesis because of the load balancing. So maybe we should look at the actual loads and the load balance and look at how things work out. So maybe we should look at the length of the queue at different processors. Okay, and this is why you don't want to just look at the answer, because the answer was COSO was better, but not COSO star. So if we start looking at the queue length in COSO versus the queue length in COSO star. Now, this is, by the way, depending on how we look at it, really bad presentation. Does anyone notice anything wrong with these plots? This is classic, but okay, so that's definitely a problem. But it's queue length, right? And this is over time. But okay.
They're not the same scale.
They're not the same scale, right? Notice this one. This is at 30, and this is at 50, right? So depending on how we look at it, this is either making COSO look bad because the top of COSO is about the top of COSO star, right? Well, really, COSO should go much higher, right? So scaling in graphics is actually very important, but this was just easier to put together. That's the two plots we had. So unless the processor starves, which happens here. So for this particular run, there was a time when there was a processor that was idle, okay? And if a processor is idle, then I'm wasting time. But if no processor is idle, they all have a long enough queue, then it doesn't really make much difference if I'm load balancing or not, because they all seem to have about a queue. Now, it might seem if jobs came in, and I'll come back to that in a different way, that might not be true. But if jobs are generally entering the network randomly, right, then random things sort of make it so that they end up at similar amounts of time, okay? And some of these processes are actually finishing faster because they had less load, right? So anytime I have multiple processes at a particular location, I lose efficiency to processor swapping, right? One in, one out, one in. So if I'm going through 10 processes, I might actually be slower than if I'm going someplace else. So, so unless it's star for surprise, there's no real advantages to load balancing. So COSO star is not actually better than COSO. We had this hypothesis in this particular set of data that wasn't true, right? So when we look at things in lots and lots, I'd say the majority of computer science problems, we really have time, right? Our experiments are running over some period of time, and we want to make sure we're modeling that in a meaningful way. So when we talk about time series, we can look at them. So this variable is time, and this is queue length, right? You'll sort of see these dynamic patterns. Those patterns are often very insightful to what is your system actually doing. Now, so if we're trying to go back and look at this, right, now we've looked at those time variables, we might want to look at the data differently and change our hypothesis. So coming back to looking at those experimental data, right, so COSO star was statistically no faster. That's not bad, right? COSO star is not statistically faster than COSO. Right? They were about the same. If I look at the distribution now in time to complete a job in thousands, right? And this is the number, the time to complete jobs, and this is how many jobs are in those categories, right? Do you notice anything about those plots? If you were running this experiment, you saw these two plots, we've now looked at them differently. How many jobs finished in how much time? Do you notice anything between COSO star and COSO? Scale. So there's a slight difference in scale. This is now better, right? This is 70 and that's 70. So there's a little bit of difference there. But do you notice anything else about the data? So where do you think the average in this data is? Okay, so the average in this data is somewhere like over here in both plots. But in fact, we mentioned this before, right? Over here, there's a few more points way out on COSO star than on COSO, right? Those few points drive the average higher for COSO star, even though there's lots of points down here. But COSO has more points finished really, really fast, right? So there's extremes at both ends. COSO has more really short jobs. COSO star ended up with a few more much larger jobs, right? So balancing wasn't the right story to tell for this data. So outliers dominate the mean. So the statistical test itself wasn't meaningful, at least as we described it. So maybe the right thing is to look at them differently, right? So these are the outliers at both extremes, right? And they're driving what's going on. So we already went through statistics. So got to recognize that the means are sensitive to outliers. So maybe we should have just changed our metric. And if we do, instead of mean time to complete jobs, do median time to complete jobs, now we get that COSO star is faster. Okay, so looking at the with means, COSO star was 4% slower, but looking at with medians, which are much more robust against outliers, it's 11% faster. Right. So now, when we talked about being better, right, even if we said faster, we actually have to be much more precise in our experimental definition. Faster on average, faster on median. Right? Is the median faster? And the answer to which of those is the right measure, well, that depends on your problem, right? If you're willing to live with some processes taking much longer, right, then maybe the median is fine because you don't mind the outliers. On the other hand, maybe you do care about the outliers. That's the same size, right? So again, we can talk about the median quartiles. We can look at them in multiple places and play some games. We already talked about those, so I don't want to go into details. But so if we started off with our hypothesis that it takes longer because COSO balances the load better, now we're down to its mean is longer, and which is no evidence that the load balancing helps because there's almost no processor starvation in this experiment. Right? So if I'm worrying about balancing load, but they always have loads, right? So is balancing the difference between a load of one waiting process and 12 waiting processes really that important? Maybe the problem was we should have run some experiments that had lower loads, right? So coming back to your experimental design, looking at some of your data, you can have a new hypothesis. So it's this kind of thing is an example of you're running a pilot experiment. So if we look at that, and this is something I recommend for whatever you're going to do, choose some smaller set of data, some smaller experiments, and run that first, and try and analyze it. Because if it doesn't work for the small ones, it probably isn't going to work for the large ones. Although sometimes that's not true. Sometimes you're much worse if you're doing a comparison for small scales, but much better at large scales. But then that should be your hypothesis. So the answer to these questions of a pilot is always, you want to run a pilot to help you understand what your hypotheses are. So in this particular case, the independent variables weren't set in a way that caused process starvation, so you really couldn't test that it was better with a star. So if you looked at that experimental data, you can go back in and sort of say, okay, since there was almost always a waiting queue, let's run another experiment varying the number of processors in the rings. Once again, so now we can run it so there is starvation, you get some things. You still show, I'm not going to go through the details, you still don't get enough differences to have a statistical difference in runtime. Okay? And the reason for that turns out to be that your algorithms have these large tails. If you think about what those histograms look like, just looking at this is actually a clue to me that your experiments are going to have a hard time reaching a conclusion because you have so much in this tail. This tail is going to dominate lots of things. Right? And so yes, with medians you might get there, but even with medians, when I go to do a statistical test, variance matters. So the spread matters in our experiment. So we want to try and do some things to try and reduce that. So even if I have the means and the medians, right, this tail is having a big effect. So you want to transform this to correct the influence of the problem. So I want to be a little bit careful here because notice we put the correct in quotes, right? If we're going to try and correct the influence of the tail, what have we just assumed? We assumed the tail isn't important, right? But there are lots of problems for which the right metrics are things like maximum time to completion, not average time to completion. If I'm flying a plane, I want to know that the maximum time for the system to respond to this critical thing is before I crash, right? Not the average time before that, right? So depends on what your problem is. You have to think about what they are. But assuming you can work with that, maybe we can play some games to work with the data. So if we were to take this and make the runtime depend on the number of processors and the job size, right? The relationships between these runtimes are different for COSO and COSO star. So if I start plotting these as linear functions and look at the size versus the runtime, for a small problem, they're identical. But as we start getting to larger and larger problems, so if I have 20 processors, right, I get a new line for the COSO star, which is in red, right, which is lower. So the runtime is now fitting a line, right? So this is one of the two ways we can try and reduce variance, which is to separate the problem instead of treating everything as one giant distribution, set it up as two different models, right? And now I can answer the question in terms of these models. So for a large number of processes, I have a good model for red. It's very linear, right? And I have a good model for green. It's quite linear as I look through the size of my problem with a different number of processors. So for many processors, as I vary the size of the problem, I have better scalability of COSO star. That's not quite the same as our original hypothesis, but there's a new hypothesis. And if we're really trying to understand the problem, we can then think about what's causing this and how can we work on that. So if I look at the runtime, the number of processors versus runtime, the runtime decreases with the number of processors. And so COSO star appears to use them better, but the variance can actually still be very high. So there's a large confidence interval. So even though we get out here with a large number of processors, COSO star, in fact, at this point, might actually have a higher average, but has a much larger variance. Okay? That variance is still going to cause a problem for hypothesis testing. But can we then ask the question, can we transform runtime with some function of the number of processors and the size of the problem? So instead of trying to answer the question in raw time space, let's transform it by having some model, okay? And if we have that right model, and we already tried to suggest here, this linear model might be a nice way of trying to separate them. So if we want to transform the runtime, we can think of the number of tasks to be done, the number of processors, the time to do all of them. So we know that if we let k equal s divided by n, that's the theoretical best possible time for this. That's perfect use of parallelism. If we do ti divided by k, we're looking at how much worse than a perfect particular runtime is our system. So if we have n processors, we're now measuring the parallel efficiency. How close are we to the optimal efficiency? So if we do something like that, then we can do a transform to a new variable that takes ti divided by ti times ni divided by si. This restates the problem in a way that's independent of the size of the problem and the number of processors, both of which cause variance. So in this experiment, when we're looking at the raw data, right, here, some of these runs, right, had more data, some had less, causing a lot of variation. That amount of variation made it hard to decide if something was better. If we transform, if we transform our variable by normalizing them by some of the variables that we have control over, right, we can now have something where we end up getting a small difference. So in this case, we have COSO has a mean of 1.6 with this new measure, and COSO's median is 1.18, and COSO star has a mean of 0.14, but a median of 0.04, right? So notice now that with this new transform variable, COSO star is better in both cases, okay? And it's nearly perfectly efficient. A perfect efficiency would be 1, right? So its median means that for almost all the problems it ran on, it was really close to being the perfect use of all the resources, where COSO had a much less efficiency. So another way to sort of graphically highlight that difference and quantify some of it is to then take something like that and do a whole bunch of random trials, and then we can look at the CDF, the cumulative distribution function, for those saying, what is this now small distance metric over many, many trials, and accumulate that. So here at 100 trials, there's a gap. By the time we get to 150, we have a much larger gap. It's now visible to the audience that COSO star over many, many random trials is doing better. Okay. So now a slightly different version of this. Talk about what the cumulative distribution function, of course, is just one way of looking at this. How else might we try and turn this from this, okay, here we have some data. How do we actually answer now if this new transform variable really is meaningfully different? Okay, so this is visually giving you some idea. What do you think is the thing we should really be doing? What did we do last week? Statistics. We want to do statistics. No one wants to do statistics, but we have to do statistics. So if we were to assume that COSO is COSO star, that's our null hypothesis. Okay, we run the statistics. We run this. We get the sample statistics, and in this case, we get a delta of 0.21, right? 1.16 and 1.4, which are the median or mean scores, not the median, right? We can find the distribution of this difference under COSO, the null hypothesis. Using that, we can find the probability, and then if the probability is very low, we can reject the null hypothesis. We went through all of that last week. In this case, 0.02 is your residual uncertainty that maybe they actually are equal. Okay, so if we do this, this is what kind of test? T-test. So you basically are taking the difference between the means, dividing by the variance, and then testing it, and that gives us that the p actually is less than 0.2. We're not going to go through all the math to do that. Again, you just use a calculator to do it. But this is an estimate of the variance between the two means, and that says that these really are statistically different. So that gives us residual uncertainty. So do you think there's anything we could do better? So the t-test I told you last week is okay, but in lots of computer science, we can do way better than a t-test. What's better than a t-test? No, not ANOVA. Paired t-test, yes. Right, so you want a pair to go with it. So if we want to do a pair test, right, we have a much stronger thing, because if we choose to, we can send exactly the same loads to both algorithms. Right, so instead of running two different things, we can give them exactly the same data. And in fact, for this particular thing, if I were to do that, Cohen eventually published this later, but instead of a p of 0.02, right? Notice 0.02 is a weird number. We never talked about 0.02 last week. Why? Well, this is not significant at 0.01, and it is significant at 0.05, but 0.02 is a little bit better. We like to use something close. It turns out that you can get a 0.001 statistical difference if you do this as a pair t-test. So by pairing them up, this run versus this run, in almost every case, COSO star is equal or better. It's not always better, but it's equal or better. It's rarely worse. There's only a few cases where it's worse. And so we already talked a little bit about the statistical tests, and we'll skip over that. And so the next part of Paul's material that I want to use is going to take way too long. So we'll call it a day here, and see you guys next week. So I'm going to be on the road. If you send me email, expect probably a 24-hour delay before I get an answer, because I will probably read it only in the mornings and then be offline all day, so, in Pacific time.
Did you see, well, obviously not since you've been teaching, to turn off your recording thing?